Hi, so I am Ruduraj and I have crafted this course to make the most complex thing of simulation into the simplest one. Have you ever wondered how to simulate systems that powers modern technology from electric vehicle to drones? It all starts with Simulink. This is your beginners to advanced MATLAB Simulink course where you will unlock full potential of MATLAB Simulink. We'll start with the fundamentals of Simulink, then we'll dive into signal generation and processing, Simulink blocks, and logic implementation. Next, we are going to learn power electronics and power system, measurements and analysis. And then we'll even explore applications and code generations from Simulink. So now without doing any delay, let's get started to the course. Hey, welcome back to another video on video lecture series on MATLAB tutorials. In today's video, we are going to talk about this tiny little block. It looks very tiny, but it is huge in size. It makes a big difference into the field of research and technology. So first, we are going to know what is Simulink. You know, Simulink is also developed by MathWorks, who developed the MATLAB. Basically, MATLAB was first introduced in 1984, before I was born, and Simulink was first time introduced with MATLAB in 2002. Today, we have much more advanced and mature version of Simulink. The latest stable version of MATLAB Simulink is 10.2. Now, the question is, what is Simulink? Basically, Simulink is a simulation and model based design environment which is specially made for simulation and analysis of multi domain system, and all this thing is done through graphical way. Yes, this is what Simulink is. Simulink has graphical blocks of physical systems. So one can directly drag and drop the blocks and connect them together to form their own system. And then they can analyze and study the system for improvement and understanding. So Simulink is used a lot across the world for understanding, for analyzing, for technological development, for research, and many more. Now let me show you a few of the applications of Simulink. Simulink is widely used for power electronics applications, control system design, industrial automation, automobile applications, aerospace applications, signal processing, physical modeling, and many more. We have discussed few things about Simulink. Now let us explore the Simulink, right? So when you are going to open the Simulink, there are two ways you can open a Simulink. The first way is on this home tab, you can click on the Simulink button and the Simulink start page will pop up. The another way is you just write in command window and the Simulink start page will pop up. Now here you can see this open button. When you click here, a window will pop up and you can open your previously saved files, right? Your previously saved models, you can open it through this section. This section shows the recent files. The recent files that you have worked with that can be seen over here. Over here, you can go for the recent projects. Whatever project you are working on, you can save those projects in this section and you can open it from here. Now we'll come to these two tabs. This tab provides us pre-designed templates which you can directly use to create your project. Over here you can see there are different types of Simulink models, communication system, DSP system, embedded system, powertrain blocks, and so on. So there are lots of pre-decided templates which is available for new users. So we'll just quickly close it for some time so you can have a full look. You can even create your own template which you want to frequently use, right? We are not going to discuss how to create your own template. For that we'll make a separate video if you want to learn how to make your own template which you really want to use frequently. So you can write that thing in comments and I'll explain how to make your own template. Now we are going to explore another tab that is for examples. Earlier, we have discussed that Simulink can be used for multi-domain applications. Over here, you can see the examples of all multi-domain applications where Simulink can be used. SimCaps Electronics, SimCaps Power Systems, Simulink 3D animation. You can see there are ready-made examples of 3D animation. Let me click it and quickly show it to you. How does it works? When we run this thing, simulation will pop up. And over here you can see how the simulation is working. So here you can see speed, longitudinal acceleration and lateral acceleration. So let's close it. So there are varieties of example available and you can select your domain and starts working with Simulink. If you are beginner, then this example will be really very much helpful for you to learn Simulink. Through this search box, you can even find the examples that you are looking for. Let us try something. Let us open this. So this is the model of three-phase asynchronous wind turbine generator. Now let us run this program. To run this program, you need to press this green run button. You run it, it will compile and simulation is done. Through this scope, you can observe the real power and reactive power quantity. Now we'll close this thing and we are going to open a new blank model. So for that you can click here and you can go for blank model. So we'll close it. We don't want to save this and we'll maximize it. Now this is the menu bar. Each of the menu bar has varieties of setting within it. We are not going to discuss all of this in detail, right? But while you are practicing Simulink, if you are having any query on any of the block and any of the parameter, then you can directly ask me in comment section below, or you can join my Telegram group where we are discussing all the issues coming in MATLAB and try to sort out the issues of the students, right? So you can even join me in my Telegram group. You can join me on my Instagram, Facebook, whatever platform is appropriate for you. You can join me there and you can ask your questions. If many students are asking similar question, then I'll probably make video on that topic. So you are open to ask me. If I know the answer, I'll definitely share it with you. So we'll start with this second bar. This button will pop up this menu. So from here you can open a blank model, model, chart, library and project. And there is a shortcut for that. Control plus N will pop up a new blank model file. Through here you can open previously saved your models. The next is to save your current model. We have yet not saved this model, so when we click this thing, it will ask us to save the model. So let me save it, and let me save it in a wrong manner. I'll give it name my space simulation, and I'm going to save it in my folder. And this error will pop up. My simulation is not a valid model name because it is not a valid MATLAB function name. So the problem here is I have intentionally provided space between two letters. So remember that you cannot provide space between two letters. So my underscore simulation and now save. So the name is done. Now this button is for library browser. When you click it, you can observe graphical blocks of multi-domain. The list of all domain is provided over here. This is Simulink. In this Simulink, you will find there are varieties of headings like commonly used blocks, continuous blocks, dashboard, discontinuous, discrete, logical, lookup table. Varieties of block sets are available in Simulink. Let us explore this sources. This is the set of sources. You can find a step source, sine wave source, ramp, pulse generator, constant, clock, so many things you can find it here. Let us take any of this. This is the sine wave block. We'll just right click it and we'll add this block to my simulation. You will click it, then it will directly add this thing to the block. This sine block is here. Let me show you another way how you can import any block to this Simulink model. Just double click and start writing the name of the block. So we want to import another sine wave, so we'll write it sine wave and click. So another sine wave has been imported. When you hover your arrow onto the sine wave block, it will ask for the amplitude. It is the amplitude of your sine wave. By default it is 1. If you want to change, you can change it to 2, 3 or whatever number you want to give. Let's make it 3. So the amplitude of this sine wave is 3 and this sine wave is by default 1. For example, if you have missed to enter the amplitude, you can anytime double click this block and set the amplitude. In this block, you can set varieties of quantity. Right now, we'll be focusing only on amplitude. Amplitude is 1. Later on, we'll see how to change this quantity as per our need. Now, I'll quickly prepare a simple model and then we'll explore the rest of the things. From here, you can directly search for any block. For example, sum. So when you search here, it will show the variety of result which has the word sum. Let us tag this block. So this block is here. Now we want to observe the result of these two.
Hey there, I am thinking to provide two things. First, a free certification MATLAB course, and a second, in depth structured course with exclusive content, exercise, and support which goes beyond what it's available here, and that is paid MATLAB course. So please let me know by commenting or filling out the interest form in description box below whether you are interested in free certification course or in paid course. Thank you so much.
Now we'll add these two together and then we'll see the result. To see the result, we are going to use the scope library. In sync, you can see varieties of output displaying devices. So from this, we are going to select this scope. So this is the scope. When you run, you can see the result in output. Now this button is for model configuration parameters. You can configure different parameters of the current model. You can set the solver, simulation time, starting time, stop time, the types of solver you want to use. There are varieties of solvers. These are different solvers which are used for different applications. We will make a separate video to understand which solver is best suitable for which type of simulation. This is the variable step or fixed step type of simulation you want to do. If you want to import the data, you can directly import data into this simulation file. You can even export the data from this simulation file. You can do varieties of things from this configuration parameters. The next is Model Explorer. It will give you the idea of different block set in the model. And this is the tab through which you can run the simulation. This is the time of the simulation. You can set it to any of your required time, 5 second, 2 second, 10 second, whatever you want to adjust. And the rest of the things we are going to explore in our upcoming videos, so stay connected to this channel. Now on this left hand side, you can see there are varieties of button. Through this button you can zoom in this model. This is the fit view. If you click it, it will adjust it to fit view. Through scroll button you can zoom in and zoom out. It is zoomed out a lot. Just click this and it will adjust to a fit to screen view. Then from here you can add annotations. You can click here and write whatever you want to write over here. Click here, you can place here, you can write signal or whatever you want to write. This is the block where you can place area and write whatever notes you want to write. You right click it, you can adjust the font style. There are varieties of font styles are available. You can adjust the size of the font, italic, bold, and different varieties of fonts you can choose. By right clicking you can even select the varieties of color you want to set. If you want to set any particular color, you can set from here. You can insert image in this simulation. You click it, click over here, double click it, and it will ask to insert image. Click, select any of the image and open it. You can resize this image. There is a shortcut to set the fit to screen. Just enter spacebar and you can adjust your simulation to fit to screen mode. Now let me remove these things. Now at the bottom you can see view marker, right? From here you can set view marker. Now let us understand what exactly this view marker is. When you are having a large system, you can use this view markers. Let me insert again sine wave, right? I am just inserting random blocks, right? So we have varieties of blocks over here. I will select these two blocks, right click it, and I will create a subsystem, right? So this is a subsystem. I'll double click it, and here you can see these are the different blocks. Again, I'll enter a few of the things over here. For example, sine wave, and again summing block, right? Together this will create another subsystem. So here, this is our main simulation. There is one subsystem within it, another subsystem within it. Now if you are having a large system and you want to work in this subsystem and then you want to go again back to that simulation, then back and forth it will take too much of time, right? And it will become a little bit tedious when you want to go back and forth very frequently. So for that, this is the solution. You can set this as a view, right? And from here, view marker, you can set this as a view marker. You click it and it will save a view marker. Double click this subsystem, again click it, it will save this view as a view marker. Again go into this system and it will set this thing as a view marker. Click it and it will save a view marker. So we have set 3 view markers. Only going back and forth is not the purpose of this view markers, but to set you in that particular predefined view. That is the fundamental use of this view marker. For example, we are in this system. We'll go to view markers and we want to jump to this. Just click it and you will directly shift it to that point. Something else and you will be directly shifted to that point. The same thing you can do from here also. When you click this point, it will open a model browser. You can directly jump from one mode to another mode. But when you jump it from here, see, you can see another section is being out of the window, right? But when you jump it through view marker, right, it will not happen that way. This is your present view, right? And jump it through view marker, so it will bring you back into that particular view. The same back and forth you can go from here also. Any of the subsystem you can jump from here. If you do not want to see this thing, just click here and it will disappear. So there are lots of things that you can do with this Simulink. I have just made this introductory video, a very basic information about Simulink. In upcoming videos, we are going to discuss a lot about Simulink, varieties of simulation about Simulink. If you want to learn anything particular, if you want to do any particular simulation, then you can write that thing in comments below, and if I know, I'll definitely make video on that topic. We are going to learn how to prepare a simple circuit in MATLAB Simulink. We are also going to learn how to measure voltage and current in DC circuit as well as in AC circuit. And we are going to explore different components in Simulink circuit. So there is so many things in this video for you. So stay tuned till the end of the video, learn from this and enjoy the video. So without wasting time, let's get started. So this is our blank Simulink model file and we are going to prepare a simple circuit using this. For that, we'll explore this library browser. So let's explore it. Once we open it, you will find a varieties of blocks available in this library browser. What we are going to use? We are going to use all the components available in SimCaps. So let's go to that components. In SimCaps, we are going to explore power system. So let's close it. So you will be having a better look of that. So in SimCaps, we are going to explore power system. In power system, we are going to explore this specialized technology, right? So when you open the specialized technology, you will find fundamental blocks, control and measurement, electrical drives, facts and renewables. So this is the library which we are going to use in our today's video. So when we want to make a simple circuit, we'll take a simple DC source. So to have a DC source, we'll go to electrical sources, and on right hand side we'll have a DC voltage source. You can right click it and add block to model. So this is one of the way to add the block to the model. Another way is, if you know the name of the block, you can directly import this block to the model file without opening library browser. How to do that thing? Let me show you that. The name of this block is DC voltage source, right? So minimize it. This is our model file. So you just double click anywhere into the model file, double click. So here you need to write the annotation whatever you want to add. So we want to add DC voltage source. So once you write DC voltage, all the DC voltage sources are mentioned over here. The first source is from electronic additional components, SPICE compatible component. The second one is specialized technology fundamental blocks. The third one is foundation library electrical sources. So we are going to use this DC source, specialized technology fundamental block electrical sources. Selected it. Now it asks you to give the amplitude. What will be the amount of DC voltage you want to produce through this source? Let's say we want to produce 50 volts. That's it. There we go. So this is how you can add DC source to the canvas, and the previous method that we have already seen. So we are going to delete any of the DC source. Let's delete it and go back to library. So once we have the DC source, now we want components like a resistor, inductor, capacitor in our circuit. So to have that component, you can explore these elements. So just go to the elements. So here we have varieties of elements of electrical circuit. What we want either resistor or inductor or capacitor, right? So here you can see that here we have series RLC branch and series RLC load. So out of these two, we are going to take a series RLC branch. Why we are going to take series RLC branch? If any of you can explore the answer of this thing, then this is the question for you. Why we are using the series RLC branch in this simulation instead of series RLC load? If you know the answer, write the answer in comments below. And if you do not know the answer and if you want to know the answer,
Hey there, I have provided this complete MATLAB course for free and I hope it is very helpful and valuable for you. After learning from this course or after completing this course, if you find it valuable for you and if you want to appreciate my efforts, please do consider donating. Your support will help me invest more time and resources into making even better tutorials and provide valuable learning experience for you. You can find the donation link in description box below. So thank you so much for your support.
let's add this thing. Right click, add block to the model. So here we have series RLC branch. So let's prepare a simple circuit. When you double click it, you will be having different parameters: branch type, RLC, RLC, RL, RC, LC and open circuit. So these are the different possible combinations which you can set in series RLC branch. If you take RL and apply, this will change to RL branch. If you want only resistance, then select only R and apply, then it will become only resistance. From here you can set the magnitude of resistance. Let's say we'll keep it as 3 ohm, right? So the resistance is 3 ohm. We'll rename it from here. Let's say R. Now when we want to prepare a circuit, the another important thing is DC voltage source. Double click it and you will be having this parameter. You need to set the amplitude of DC voltage. Here the by default value is 100, so we'll keep it as 100 only. Okay, Now we are going to connect it. So drag it, connect, left click, drag and connect. Generally this type of arrangement we do not like to see. So what we'll do, right click it, and over here you can see rotate and flip. So clockwise rotate, click, and the resistance is rotated to clockwise direction. I'll give you the shortcut key. You just select it and press Ctrl plus R. So it will rotate clockwise. Ctrl R, rotate clockwise, Ctrl R, Ctrl R. Right? So this is the shortcut to rotate it clockwise. This circuit looks very simple. So what we'll do, we'll add one more resistance. So we'll delete it. So we'll copy it. Ctrl C, Ctrl V. When you bring this thing in front of this, over here you can see the light blue line. This light blue line indicates that here there are 2 points which you can connect directly without dragging the connection. So just go there and click over there on blue line and the connection will be established. If the blue line does not appear and still you want to connect two things without dragging the line, then there is a simple way. Click over here, press Ctrl and then click over here, and there we go. This is another shortcut to connect the components. Now this is our simple circuit is ready. We'll open it. We'll change the magnitude of resistance. Instead of 3, we'll make it as 15. So everything is ready, the circuit is ready, but now we'll see how to measure voltage and current in the circuit. For that, we'll again go back to the library browser. Here you can see that there is a measurement tab. When you click the measurement tab, you will be having all these instruments. Current measurement, so right click it, add to block. Voltage measurement, right click it, add to block. So here we have voltage measurement and current measurement. So emitter we always connect in series, so we'll connect it as like this, and this line will delete. So we have connected this current measurement, and now we want to measure the voltage, right? So we'll just adjust this circuit a bit, right? So to connect this thing, we'll drag. So connection is ready. This is for voltage measurement and this one is for current measurement. But now we want to observe that what will be the reading of this voltage and current. So to observe that thing, we require a display. Let's come back to the library browser. Go to sync. Over here, there is a tool called display. Add to the block. Here we have a display. Connect it, duplicate it, Ctrl C, Ctrl V. Bring it over here. Click on current measurement, press Ctrl, click on display, and the connection will be established. Now the circuit is ready, but remember that whenever you are running simulation through SimCap's specialized technology, you need to add one more block that is known as Power GUI Block. You can find that block directly from the library browser. Here there is a specialized technology. Click on fundamental blocks and there is Power GUI Block, or else you can directly double click it and write Power GUI. Here is the block, right? And now let's run the simulation. So here we have the voltage 16.67 volts and the current is 5.56 ampere. This is one simple way to measure voltage and current. Now I'll show you even more simpler way to measure voltage and current. Let's go back to the library browser. Here go to the measurements. In measurements, here we have very fantastic instrument called multimeter. Let's add this thing, right? We have a multimeter here. Double click it. Right now the available measurement, nothing is available. Selected measurement, nothing is selected. Close this thing. Right now there is nothing available in multimeter to measure. So first we need to give signals to the multimeter that these are the available signals, and then this multimeter can measure those signals. Double click this resistance and over here you can see the measurements. Click on that, you will see branch voltage, branch current and branch voltage and current. Right now we are measuring the branch voltage. So once you apply it, the signal will be transferred to the multimeter. Once you open the multimeter, over here you can see that there is available measurement VB of R. Close this thing, double click it, measurements, branch voltage. Now we want to measure the voltage of R1 also. Okay, double click it, and now you see here we have R1 resistance and R resistance and the voltage across R1 and R resistance. So through this section you can select the different measurements. Once you select the measurement over here, that measurement will be directly reflected to the multimeter. Once you have the available measurement, from there you can select and transfer it to selected measurements. Whatever measurements are displaying on this right hand section, that will be measured using this multimeter. So we have selected the voltage across the resistance R. Close this thing, take another display, Control C, Control V, and connect. Now let's run the circuit. So without having these connections in the circuit, we can directly measure the voltage and current in the branch. After this, I would like to ask you a small question, and the question is this: what is the advantage of using multimeter instead of the voltmeter? Whatever you have observed just few minutes ago, you need to think of that and write the answer in comment section. Now let me tell you something else. Here we are measuring only one quantity. What if I'll select the second one and add it to the selected measurements? I'll close this thing. Now we have two quantities that we are measuring, and that number will be displayed on the display of multimeter. But here you can see that we are having only one display. We are measuring two readings. Now what will happen? So let's see. Run the simulation. Second display will be automatically popped up after the simulation. Just drag it a little bit below and you can see the voltage across resistance 1 is 16.67, that is displayed over here, and the 83 is across the R1.
Hey there, I am thinking to provide two things. First, a free certification MATLAB course, and a second, in depth structured course with exclusive content, exercise, and support which goes beyond what it's available here, and that is paid MATLAB course. So please let me know by commenting or filling out the interest form in description box below whether you are interested in free certification course or in paid course. Thank you so much.
Let's suppose over here we are measuring voltage and current. Make it okay. Here we have IB. I represents current. So IB, the fourth quantity is current, and over here we are measuring branch voltage and current. Here we have IBR1 and we are adding it. The first is voltage across R, the second is voltage across R1, the current across R, and the current through R and the current through R1. Close this thing. We are measuring total 4 quantity. Run this thing and there we go. The voltage across R1, voltage across R2, current through R1, current through R2, and here you have a verification check that through this emitter it shows the reading of 5.556, through this 5.556, and through this 5.556, because this is a series circuit, right? So the current remains same throughout the circuit. So this is how you can measure voltage and current in a simple circuit. Now we are going to do something tricky. We are going to add AC source. For that we'll go back to library browser, and here we'll go to electrical sources, and from that we'll bring AC voltage source. We'll add to the model. This is our AC voltage source. We'll connect it over here across the DC source, and then we'll delete this DC source. So now our circuit will be having AC source. So this is our AC source.
Here we need to add peak amplitude and frequency. So I'm going to change the peak amplitude and frequency. But before changing, I'd like to ask you one thing. You just guess two values, right? Peak amplitude and frequency, right? Just imagine two values in your mind. And now I'm going to write these two values over here. If the value you imagined and the value I'm writing are same or very close to each other, then write same in comment section below. Or if it is not same, then write just missed it in comment section below. So we'll have the fun, right? It is nothing important, it's just for fun, right? So I just want to imagine that how closely I am connected to you all, right? So now I'm going to write the value. If the values are same, write the same in comments below. And if it is not same, write just missed it in comments below. 220 volts and 50 hertz. And there we go. Now I'm going to run the simulation. Oh my god. We have given 220 volts and across this resistance the magnitude is 2.44 e raised to minus 12. 8.14 e raised to minus 13. My god, there is something wrong. Now let me change the value over here. Let's say 8 seconds instead of 5 seconds. Run it again. My god, again the value has changed. Here it measures all the instantaneous value. This also measures all the instantaneous value. It directly reflects all the instantaneous value it measures to the display. So here the magnitude that we are observing is the last measured value, right? So the last measured instantaneous value through this AC source is this much. But when we are dealing with AC, what we're supposed to measure, if you know that thing, then write in comments below. We're supposed to measure RMS quantity, right? But here it shows the instantaneous quantity. So what we're supposed to do, we're supposed to convert this instantaneous to RMS and then measure. So again go back to library browser. So this is our library browser, and here from where we'll go to measurements, and through this measurement we'll go to the additional measurements. In additional measurement you will find this RMS block. Right click it, add to the model, and here we have the RMS block. Just drag it, delete it, add this in between, click, and done. Copy it, paste it, drag it, delete it, place it in between, click it, and there we go. The connection has been established. Run. There we go. So here now we have the appropriate answer, the RMS magnitude, the RMS value of voltage and current. So but here we forgot to add the RMS, right? So what we'll do, just drag it, delete it, copy RMS, paste it, place it in between, and connect it, run it again. That's it. Here we have the RMS voltage and current. So this is how you can measure the AC quantity, AC voltage, AC current in a simple circuit. Now one more interesting thing I want to show you, and that is when you double click this multimeter, over here you can find this small tiny important thing, plot selected measurement after simulation. Just click it and close it and run this thing. The graph window will pop up and it will show you the waveforms of all the quantity, voltage and current across the resistance and through the resistance. Uh, expand it and zoom it, zoom it, zoom it, and zoom it. So you can even observe the waveform. There is one more way. If you want to observe the waveform, there is one more way. The more effective way is observe it through the scope. Let me show you that. This is our library browser. Go to the sync. In sync, there is another block is known as scope. Add that block. Here we have the scope, right? Drag it here, and now you will be able to see the instantaneous voltage, the pure sinusoidal voltage waveform of the voltage. Over here it shows the RMS of all the different quantities. So we'll double click it, and from here numbers of input will make it 2. So here we have 2 inputs, we have connected voltage, and now we are connecting the current. We have connected instantaneous voltage and current. We'll run the simulation. The graph because of multimeter, and this is our scope. We'll expand it horizontally, so you will be able to see the waveform of voltage and current. The yellow is voltage and the blue is current. You know friends, this scope is really a fantastic thing. Almost all the simulation, or I can say more than 90-95% of simulation contains this block within their model file. We are going to explore each and every detail of this scope. First we'll go for this toolbar, all the details in this toolbar, complete details, and then we'll go for this menu bar, file, tools, view, simulation, and help. So without wasting time, let's get started. So this is the blank canvas, and we are going to prepare a simple circuit. To add different blocks to this canvas, you can go to this library and you can take any of the sources. For example, we are going to take the sine wave, add to the block, and here we have the sine wave. There is another way through which you can add another sine block to this canvas. Double click it and write sine wave. So here we have another sine wave block, right? Now I want to add these two sine waves together, so I'll double click it and write add. I'll have another block. I want to add these two, so I'll make it plus plus. So there we go. Now it's time for the hero of the video, scope. So let's add scope. Right now we want only one axis, and there we go, our circuit is ready. It looks so tiny. So if you want to make it a little larger, I'll give you one shortcut. Just press spacebar and it will automatically adjust it to fit to screen view.
Hey there, I have provided this complete MATLAB course for free and I hope it is very helpful and valuable for you. After learning from this course or after completing this course, if you find it valuable for you and if you want to appreciate my efforts, please do consider donating. Your support will help me invest more time and resources into making even better tutorials and provide valuable learning experience for you. You can find the donation link in description box below. So thank you so much for your support.
Now let us adjust the parameters. Amplitude 1, frequency 1 radian, that's fine. Here amplitude make it 2, frequency also 2, and run the simulation. There we go. Double click it. This is how the display of scope looks like. Now we are going to explore each and every tools in this scope. Now we'll rearrange this scope and observe each and every details. So here our view is ready. This section is the display of scope and this section is our simulation model. First we'll start with the configuration properties. Over here you can see a tiny gearbox. Click it and you will have the configuration properties of scope. There are main 4 tabs: main, time, display, logging. We'll start with the main. In main, the first thing you'll find is open add simulation start. When you click it and press apply, this simulation display will automatically turn on once you start the simulation. What we'll do, we'll close it too, and we'll run it again. And you can see the window popped up automatically. If you unclick it, close it, and run it again. The window did not pop up automatically. So you can understand the difference. The next is display the full path. If you click it, it will display the full path. Full path means we are running simulation for the 10 seconds. So it will show the full path of 10 seconds. The next is numbers of input ports. Here we are having only one port. If you want to observe the multiple signals in one scope, then you should increase the numbers of ports. Here we have one signal which is addition and the two signals which are our raw signal. So total we have three signals. So let us add two more numbers of input ports and make it three. Okay. So right now we are having total three inputs, right? So what we'll do, by dragging you can increase the size of the scope. You can connect this signal to the scope by left clicking over here and dragging it up to the signal. Another way is, if you want to take a branch from here, then right click at this point, drag a branch, leave the right click, left click, drag it to the point. So this is another way through which you can take a branch out from any signal. And then finally we will have the final signal. We will just rearrange these things. Now we'll run it again and we'll observe all these three signals in scope display. So there we go. You can see all these three signals are displayed in the scope. Over here, the first question comes into your mind is, how should I identify that which of the signal is which in this output? From here, you can add legends. Click on the show legends button and you will have a legend over here. So yellow is the sine wave, blue is sine wave 1 and the red one is add. So here this one is the sine wave, this one is the sine wave 1 and this is the output of add. So by observing these legends you will be able to identify the output. Now we'll jump back to our configuration property. So we have seen how to add numbers of input port. Now we'll go for the layout. When you click this layout button, a small window is popped up over here. Here, each of this block changes its color when you hover the mouse. This shows the matrix layout or arrangement of all these three graphs. This means a matrix of 3 cross 2 is placed in this figure, and you can place up to 6 figure in one graph. Just click over here and say OK. So you can observe that 3 rows and 2 columns, so total 6 figures you can occupy in this place. Let's click it again. Over here, when it's blue, it means this place is assigned to any particular graph. But when you shift over here, the gray color means there are no graphs to put in that place. So now I'll modify my layout. I'll just make it 3 cross 1 and apply OK. So this is how my 3 cross 1 layout looks like. Again, we'll go back to configuration properties. The next is sample time, input processing. There are two options: column as channel, frame based, and element as channel, sample based. The next is maximize axis. What will happen when you change this parameter? It is off right now. So you can observe there is a gap between two graphs. When you turn it on, it will maximize the axis and there will not be any space between the two graphs. If you off it, it will give you some space between the graph. The next is axis scaling. Right now it is in manual mode. You can make it auto or after an update. If you make it auto, it will automatically adjust the axis properties. When you make it manual, you can configure the axis scaling properties. To configure it, you need to press over here configure and this will expand. From here you can configure the y-axis and from here you can configure the x-axis. Let us configure it and observe how it changes. Right now the y-axis property is set as 80% of the area will be occupied by the signal. If I make it 25% and apply. Once you run it again, you will be able to see the difference. The magnitude of signal remains the same, but automatically the scaling is adjusted to so high that our signal will only occupy 25% of space into a graph. If you make it little larger, if you make it 50, run it again, then the scale will be automatically adjusted in such a way that the signal will occupy the 50% of space into the graph. The same way you can auto scale x-axis also. It is 100% right now, and that is why we are getting 100% signal. If we make it 50% and apply, and then let's see what happens the next. The signal will only occupy 50% of the space horizontally. So again we'll make it 100%. Run it again. So this is how auto scaling of the axis x and y functions. The next tab is time tab. So we are going to explore it now. We'll make it 80, and now we'll explore the time tab. The first thing is time span. Here it shows auto. That means the time scale will be automatically adjusted to the full simulation time. If you want to change it, you can make it user defined from here. You can define your timestamp. For example, we are applying as 5, and once you apply, you can see it will show only from 0 to 5 seconds, from 0 to 5, 5 to 10. So in that band it will show the time span. If you have set any time span less than the full simulation time, then in time span overrun action there are two options: wrap or scroll. If you have set scroll, then it will scroll while the simulation is being running, or in wrap it will directly snap from 0 to 5 to 5 to 10. The next is unit. You can set it to metric or seconds. Then the time display offset. I'll show you this thing, but first I will go for this time axis labels. Right now the option is bottom display only. So you can see that the time scale is only visible in the bottom graph. You can change it from here to all graph, right? So now once you apply, all the axes will be having a separate time scale on its graph. Now here you can set show time axis label. So once you click here and apply, it will show time on x-axis. So now I'll explain this thing, time display offset. It starts from 0. So if you want to start this graph other than any 0 value, then you can set it from here. Let me make it 2. Apply. So now you can see the graph starts at 2 and will go up to 7. Right? So this is the display offset. The time will start from the mentioned offset value. So now we'll make it 0 and we'll make it auto.
Hey there, I am thinking to provide two things. First, a free certification MATLAB course, and a second, in-depth structured course with exclusive content, exercise and support which goes beyond what it's available here. And that is paid MATLAB course. So please let me know by commenting or filling out the interest form in description box below whether you are interested in free certification course or in paid course. Thank you so much.
Now the third tab is display tab. In display tab, you can see the first thing is active display. Over here you can see a yellow border over this first graph because we have selected the first active display. So if you select second active display, it will select display number 2, and likewise you can select any of the display from all these graphs. The next is title. So from this section you can set the title. We have selected active display 3. So we'll give title it as addition. Apply. So it shows the addition. If you select display number 2, so this is how we can give title to each of the graph. So from here you can make these legends visible or invisible. You unclick and apply, the legend will disappear. So from here you can make these legends appear or disappear. You just unclick it, apply, and it will disappear. So if you want to see it again, just click it and apply. So you can see the legends are available now. From here you can turn on this grid, click, apply, the grid disappears, click it back, apply, the grid comes back. So from here you can have the grid control. From here you can set the y minimum limit and y maximum limit. Right now it's -2 and 2. You can see it's -2 and 2. So whatever limits you want to give, you can set it from here. And then finally the y label. From here you can set the label to y-axis. So this is how you can set the amplitude to all these graphs. The next tab is logging. In this tab, the first point is limit data point to last 5000 points. Right now I have unclicked it, but generally this point creates many issues in simulation. Many times you have found that when you run the simulation, you are not able to see the full graph. The reason is you have marked this limit data point to active. Let me do it and show it to you. Click it, apply, and run. So when the limit of this 5000 data point is enabled, you will face this type of issues. The graph will be shown of only last 5000 points. Let me zoom it out from here. Okay, I cannot zoom it out because in this main screen we have fixed the scale, right? So we will unclick it, right? Again come back here, run it again, and now you will be able to see. If you have set this limit to only 5000 points, right, it will show this type of things. Now what we'll do, we will disable this limit, we'll apply, make it 10, and then run it again. So once you have removed that limit, run it again, auto scale it, and you can see, you will be able to see full graph. But whenever that limit of last 5000 points is enabled, you will not be able to observe the full graph. So that is why this point is very important. Now the next point is decimation and log data to workspace. These points I am not going to cover in this video. Why? Because this itself requires a 10 minutes explanation. And if I do it in this video, the length of this video will become so large. So I'll make a separate video on these 2 points. But if I tell these things in brief, then when you enable this log data to workspace, you will be able to store all this graph as a separate variable in workspace. How, what, when, why, all those questions we are going to tackle in our upcoming videos. So right now we are not going to discuss it in this video. So now we have seen all these 4 tabs of configuration properties. So before moving ahead, there is a quick short question for you, and the question is this: which of the tab is useful to set Y label out of all these 4 tabs? Write the answer in comments below. I am asking this question to have just a self check that have you really learned anything from this video or not. So check it by yourself and write the answer in comments below. Now we'll jump to the next thing. Close it. Beside this gearbox there is small arrow. When you click it, a small menu will pop up. So the bottom thing shows the show legend. When you click it, it will disappear all the legends, and if you want to see it again, just click it again. So from here you can directly have the control of legends. The next thing is layout. If you want to change layout quickly, you do not need to go to the configuration parameter. From this section also you can set the required layout. The next is style. This is very important thing, because using this style tab you can style this graph the way you want. The first is figure color. So from here you can change the figure color. Let's make it white. The next is axis color. So let us make it white too. So from here you can change the axis color. Now once you have changed the axis color, from here we will change the linings and text color to black. The next is active display. So from here you can individually control each of the graph. Here it shows active display 3, so we are going to change this third graph. The name of the signal is add. So from here you can change the line, width and color. So first we'll change the color, we'll make it blue, apply. From here you can change the thickness, let's make it 2. The thickness is changed. From here you can change the different styles of line, let's make it dash line. So this is how you can change the properties of the line. From here you can select the next display. So this is how you can set the appearance of the graph. So now we are done with this configuration properties. All of these tools are just a shortcut from this menu bar. So now we are going to explore this menu bar instead of going for each of these tools. First we'll go for the files. In files, the first thing is open at start of simulation. We have seen this earlier in configuration properties. When we click it, the scope will automatically pop up when we run the simulation. From here we can set the numbers of input 1, 2, 3 or more. This is copy to clipboard. When you click it, this entire signal will be copied on your clipboard and you can directly paste this graph into your Word file. Let me show it to you. This is my Word file. When right click and do it paste, it will paste the entire graph. So this copy to clipboard is really very useful. The next in files is print, print preview and print to figure. So print and print preview is useful for directly printing to the printer, but print to figure is really very important. When you click it, this graph, the graph in the scope will be popped up in another window and that window is figure 1. So now this graph will be open as a figure, and once this is open as a figure, you can configure various properties of this graph. Like in edit, you can see you can adjust the figure properties. You can give the figure name, signals. So here the name is signals available. From here you can adjust more properties. All these properties are available over here. We'll close it. Properties of individual graph which you can regulate from here. You click on any of the graph and separate property of that graph will be popped up. X-axis, Y-axis, Z-axis, font and all the different properties you can set it from here. For each of the graph you can control the properties of that graph. You can control the color, the dashed line, the title, font style, everything you can control it from here. There are other different tools available in this figure editing block, but we are not going to explore all of these things right now, because right now our focus is to understand scope, not to understand how to edit the figures. We will make a separate video on how to make a paper ready or a report ready figures from the scope, but that we'll see little later. So right now we'll focus only on scope. So we'll close it and again go back to the files, close and close all the scope windows. So it is self-explanatory. The next is tools. From here you can zoom in, zoom x-axis, zoom y-axis and zoom out. From here you can pan the graph, pan, and you can move this graph the way you want. Basically all these properties is available over here, panning and zooming. Once you click it, starts clicking it, it will keep on zooming at that point. If you want to zoom out, click over here, you will be able to zoom out the axis. If you want to rearrange all this axis, from here you can adjust all the axis. So from here you can do horizontal as well as vertical zoom. Click zoom X, click and drag up to the point where you want to zoom in. So this will zoom in the graph like this. The area you want to zoom, just drag up to that area and it will zoom that area. Again, auto scale. If you want to zoom y-axis, select appropriate y-axis and drag up to the area where you want to zoom and it will zoom the y-axis. Again, auto scale and zoom out. From here, you can zoom horizontally, you can zoom vertically, and you can set auto scale. So ultimately, shortcut of all these things is available over here.
Hey there, I have provided this complete MATLAB course for free and I hope it is very helpful and valuable for you. After learning from this course or after completing this course, if you find it valuable for you and if you want to appreciate my efforts, please do consider donating. Your support will help me invest more time and resources into making even better tutorials and provide valuable learning experience for you. You can find the donation link in description box below. So thank you so much for your support.
Now the next thing in Zoom is axis scaling. You can save the axis limits, restore the axis limit, automatically scale the axis limit. The shortcut of these things is available over here. Scale axis limits, scale x and y limits, all these sections we have seen in configuration properties. So we are not going to repeat all these things again. The next thing is triggers and measurements. So first we'll explore the measurement and then we'll go for the trigger. So in measurement, the first is trace selection. The trace selection is basically to select any particular graph. So from here you can select any of this graph and then you will do different measurements. The next is cursor measurement. We'll select it and you will be able to see two cursors on each of the graph. So from here we'll select any of the graph. Let's select this middle one, the red graph. Now when you move this cursor, you can observe the change in the value, right? So it will indicate the value of x and y for this particular point. If you want to observe the value for any other graph, so from this trace selection you can select that particular graph and it will show x and y's magnitude for that particular point. So here it will show the time at this point. This is point number 2 and this one is point number 1. So this one shows the readings for point number 1 and this 2 shows the readings of point number 2. So right now we are at 7, so it shows 7.006 and the magnitude is 1.984. This delta t shows the horizontal distance between the point number 1 and point number 2, and delta y shows the vertical distance between these 2 points. Here there is another small section available for settings. So from here you can set from waveform cursor to screen cursor. When you adjust it to screen cursor, you can move this cursor anywhere into this screen and the reading according to that point will be visible at this measurement section. If you want to move this point only on the graph, then you need to select the waveform cursor. Then after, with the movement of this cursor, the point will shift only on the graph, and when you select the screen cursor, then it will move anywhere into the screen. So we'll set it to waveform cursor. From here you can lock the cursor spacing. If you move one, both this line will be moving, right? Because we have locked the spacing between point number 1 and point number 2, or we can call it as cursor 1 and cursor 2. Snap to data. If we want to snap to any particular data, it will directly jump to the next taken data. So we'll unclick these two things, close it. So these are the measurements which you can take from the cursor measurement. The next is signal statistics. So from this section you can have all the important statistics of the selected signal: maximum value, minimum value, peak to peak value, mean, median and RMS value for this selected signal. So all the important quantities of selected signal can be observed from this signal statistics. The next is bi-level measurement. So in this bi-level measurements, you can have multiple datas. Let me close these two things so we can have a better view. Over here, there is parameters of overshoot, undershoot. All these things are very much useful when you are dealing with the error signals, right? These are for the cycles. It shows the frequency of our signal, pulse, width, duty cycle. All these things can be seen from these sections. Now we'll close it and go for the final peak finder. In this peak finder, from here you need to select the waveform. We have selected sine wave 1. So here it shows there are 3 peaks available. Now when you click peak number 1, it will show the x and y of that peak number 1. And likewise it will show all the subsequent peaks. So this is what the peak finder is. We'll close it. Now we'll go to tools and check out this triggers. From this trigger, the first is mode. You can adjust auto, normal, once or off. Let's make it once. From here you need to select the source. We have selected the sine wave 1. You need to select the type, age, pulse, transition. We have kept it to age, rising edge, falling edge, or either any of the age, whatever you want to select. Let's suppose we are taking as falling edge. This tab is for auto level. When you click it, it will automatically level it. If you unclick it, then by clicking here you can adjust the level, right? So let's suppose we are keeping it up to this level, and let's run it again. So you can see this is how it is triggering the signal at the falling edge. Now we'll explore the next things. We'll close it, run it again. So our original graph is back again. The next is view tab. In view tab, the first is layout. When you click it, it will again show us the layout, and this thing we have already seen. The next thing is configuration properties. This tab we have already seen. Then the next is style, legend. So all of these things we have seen earlier. The next is bring all windows forward. So it will bring all the windows of the scope in forward direction. The next is toolbar. By clicking over here, you can disappear this toolbar. See, this toolbar is disappeared and it appears again. From here, you can remove the status bar, which is below over here. From here, you can highlight the Simulink block. Once you click it, it will highlight this scope block. So this view section is over. The next is simulation. From here you can run the simulation. From here step forward and stepping options and Simulink snapshot. So from here you can take a snapshot of Simulink. You can run it from here, step forward, backward, and stepping options you can adjust it from here. This is stepping option. If you enable stepping back, it will step back the simulations, right? Instead of this 250 steps, let's make it 100 steps. Apply and OK. Then step it forward. Now we'll step it forward. When you step it forward, at each click it will forwarding by few steps. Now let me change the stepping option. Instead of this 100 points, let's make it 500. Okay, let's run it again, and now we'll do step forward. So when I click, at each click all this graph will step forward 500 points, right? See, now so this is how you can achieve step forwarding of the simulation. So this simulation tab is also over. The final tab is help tab. Over here you can find the help of the scope, Simulink help, keyboard, command, shortcuts. Click over here. There are few shortcuts provided here. and different Simulink examples, and about Simulink, the details of the Simulink, you can explore it from about Simulink. So that's it. We have covered the entire scope in this video. In next video, we are going to cover log data to workspace, and then we'll play with that logged data. We'll plot the graph and do so many things in that MATLAB. And then after, we are going to explore how we can edit the figures and make it ready for the paper publication or for any other report publications. This log data to workspace is really very helpful when you are dealing with simulations. For example, you want to study this thing in future, you want to analyze different outputs, you want to store this data to use in future or to use somewhere else. There could be many reasons to store the data in workspace. So now we are going to explore that how we can store the data in scope to workspace variable with minor details and small comparisons. So now let's get started. Okay, so this is our circuit. This circuit we have prepared in our previous video. In our previous video, we have learned about scope. In that video, we have gone through all the tools in the scope, including this file menu, tool menu, view, simulation, help, as well as measurement, styling, zooming, and many more about the scope. If you want to watch that video, I'll provide the link in description box below and above here in card. But in this video, we are interested in something else. This is the data in scope, and we want to store this data into the workspace in our defined variable. And for that, we'll go to the configuration properties and logging. In logging, there is a tool called log data to workspace. You need to enable it. Once you enable it, the first thing you will find is variable name. Over here, you can give any variable name. I have already given the name of the variable one signal, and then save format. There are 4 different formats available in which you can store this data. We'll go through each of the format one by one. First, we'll start with the array. So we'll save this data as array. Once you click OK, you need to run the simulation again, and then we'll jump to the workspace. So now here in workspace, you can find one signal variable. The size of the variable is, it has almost 1 lakh rows and 2 columns. So let's explore that variable. So these are the 2 columns.
Hey there, I am thinking to provide two things. First, a free certification MATLAB course, and a second, in-depth structured course with exclusive content, exercise and support which goes beyond what it's available here, and that is paid MATLAB course. So please let me know by commenting or filling out the interest form in description box below whether you are interested in free certification course or in paid course. Thank you so much.
So we have 1 lakh and 2 rows and then 2 columns. So first what we'll do, if you want to access these variables, how you can access this variable? There are 2 ways to access the variable. One is just directly by writing the code, and the second is using this plot. So I'll show you first the simple method and then by code. So here column number 1 and column number 2. If we observe these 2 columns, right, we can see that the first column, the magnitude of first column is gradually increasing and the second column is varying. So observing these readings, we can know that the first column is time and the second column is amplitude. So we'll select entire column number 1. When you select entire column number 1, you can see that varieties of graphs are highlighted. So from here you select any one graph, right? So we'll plot this. Once you select it, you can see that on y-axis there is time and on x-axis there is numbers of readings that we have taken through the simulation. Now we'll close it. We'll do same thing for the next column. We'll select entire column, select plot, And now you can see we have the graph of amplitude. On y-axis it is amplitude, and on x-axis we have the numbers of total readings or numbers of total points that we have taken through simulation. So it is very simple to plot individual quantity, time and amplitude. But now I'll show you how you can do that thing using the commands. We'll close this thing. So if you want to access these variables manually, and if you want to plot the graph manually, what you can do, you just need to write plot, then write the name of the signal. The name of the signal is provided over here, one signal. So you need to write one signal. Then in one signal, to plot the graph, we want to include all the rows. So we'll use this gem to select all the rows, comma. Now we want to go for which column we want to plot. So we'll select either column number 1, or you can select column number 2. If you want to plot amplitude, which is given in column number 2, then you need to select column number 2, bracket over, second bracket over, and enter. And there we go. Here we have the graph. Now close it. Using this direct plot, you can plot individual columns, right? But what if you want to plot the graph where x-axis is time and y-axis is amplitude? For that, we'll make it a little bit bigger. We'll use the same command plot, but here to plot x-axis we'll use column 1 because this column is of time. So in plot x we'll use all the rows and column 1, then comma, one signal, that is the name of the variable, all the rows and column number 2, this one, and then we'll run. So this is how you will get time on horizontal axis and amplitude on vertical axis. So this is how you can deal with array format. So let's go to configuration property, logging, and now we'll check other data formats. So first data format that we have checked is array. Now let me tell you that where to use array. When you are using only one set of axes, at that time you should go for array. But when you have more than one set of axes, at that time you need to go for either structure or structure with time or dataset. Now let us explore that thing. Here we have another scope. Here we have multiple set of axes. So in this case, we'll go to logging, enable this log data to workspace. The name of the variable is 3 signals. So first we'll go for structure, right? Now before going to structure, what if I select array when I have multiple set of axes? Apply, OK, and when I run the simulation, it shows an error. Simulation does not support array format for logging multiple data, right? So here we have multiple data set of axes, so we should not go for array. Now we'll go for another type of data set, and that is structure. Now we'll run it again. So here it is, our workspace. This was our previous variable, one signal, and here it is the new generated variable, 3 signals. You can see here the 3 signal is 1 cross 1 structure, right? So when we double click it, it will pop up a window where you can see time, signals, block name. If you open time, the matrix is completely empty. 3 signals dot time matrix is completely empty. The second field is signals. It is basically a 1 cross 3 structure. When you open it, you can see that 1 column and 3 rows. This shows the dimension, label, title of the signals, and plot style. So here the data of each of the individual graph is stored in this variable 3 signals dot signals. So here in 3 signals dot signal variable, we have the data of multiple set of axes. Here you can see that we have three axes: sine wave 1 and addition. When we open this signal, the first one is sine wave, second is sine wave 1 and the third one is signals. So here when you open any of this variable, then you will find amplitude measured in various points that have been stored in this matrix. So ultimately all these things are the amplitudes. Let me plot the graph of this. We'll select this, go to plot and select the plot. So you can see that over here we have the plot of amplitude. On y-axis it is amplitude, and on horizontal axis the total numbers of reading that we have taken in scope. But one thing is missing over here is there is no time data, right? The time data is not available in this structure format. We'll close this thing, we'll open another one. Same thing here, you will not be able to see any time data. When you plot it again, you will be able to see the graph of amplitude versus numbers of points. But time is not stored in this variable. We'll close it. We'll close it. So in structure format, you can store the data of more than one set of axes, but without time. Now we'll close this thing and we'll go for the next type of format, that is structure with time. So in this format, you will save all the data that will be able to save in structure, but the additional data will be time. So whenever you want to store time with your other data, you should go for structure with time. Make it okay and run the simulation. Go to workspace. So here in workspace, we have three signals, 1x1 structure. We'll open it. The first is time, but see here you will be able to see the difference. Initially the value was 0, but right now we have a matrix of 1 lakh cross 1 double, right? So we'll open it and we'll be able to see the different values of time. There are total 1 lakh and 2 values from 0 second to 10 second. The next variable you can see is signals. So in signals, we have again the same 1x3 structure. When we open it, we'll find the same thing as we have seen previously in structures, right? All the things is same. When we open any of these things, we'll be able to get all the amplitudes of the signal. So basically, what is the difference in between structure and structure with time? It is very simple. In structure, you will have the data of amplitudes of all the signal. But when you store the same thing in structure with time format, you will be have all the data of amplitude as well as time. So here we have additional advantage that we have value of time. Now, if you want to plot the signal, the method is same. You just select any of the column, go to plot, select, and here we have the plot, right? If you want to plot the time, we'll go to time, select the signal, plot, and here we have the time. Now the same question arises again, but here the same question arises, what if I want to plot time versus amplitude? So for that it is very simple. You need to write variable's name. Here time is stored in 3 signals dot time. It is the name of the variable where the data of time is stored, and 3 signals dot signal 3 dot values has all the values of amplitude. So we'll plot the signal. And here we have the graph of time versus amplitude. So you can access any of the variable in structure with time, or in array. The thing is, you need to use the appropriate name for that particular variable. That's it. If you use appropriate name, you can use the data. To simplify it, you can store this variable into a simpler name like y is equal to and enter. So here we have a y variable. When you double click a y, you will have this 102 cross 1 data set. Clear the screen. So this is how you can deal with structure and structure with time. Now we'll move ahead.
Hey there, I have provided this complete MATLAB course for free and I hope it is very helpful and valuable for you. After learning from this course or after completing this course, if you find it valuable for you and if you want to appreciate my efforts, please do consider donating. Your support will help me invest more time and resources into making even better tutorials and provide valuable learning experience for you. You can find the donation link in description box below. So thank you so much for your support.
The next is dataset. But before we proceed to dataset, there is a quick short question for you. Your question is, what is the advantage of structure with time data format? You need to write the answer in comments below, and if you have any doubt, you can contact me by asking your question in comments, or you can directly live chat with me on my Instagram ID or on my Telegram page. So the choice is yours. You can join me on Telegram or on Instagram or on FB. So now we'll move ahead with dataset. So here we are storing all these things in a dataset format. Okay, let's run it again. Now we'll go to the workspace. So here it is, our workspace. One signal is our first simulation, y we have just created recently, and here the three signals is our variable. You can see here the name of the variable is 1 cross 1 data set, right? So the name of variable has changed from 1 cross 1 structure to 1 cross 1 data set. Let's open it. So here you will be able to see each of the signal is stored individually. 1 cross 1 signal, 1 cross 1 signal, and 1 cross 1 signal. If we open any of the signal, then in that signal we have multiple data like port, input, port index 1, propagated name, block path, values, and name. So our data is stored in these values. The format of these values is 1 cross 1 double time series. So let's open it, and you can see our data is stored with time and amplitude. So the advantage of using this data set is multiple information is stored directly with that variable. Over here you can see that there are multiple information is directly stored with this 1 cross 1 signal, right? If you open another signal, then the same thing you will be able to see. Port index is 3. So here you will be able to identify that from which scope you have taken the data, from which port this data has been taken, the path, name, values. Multiple data is stored in this 1 cross 1 signal. So it is enriched form of storing data. When you open the values, again you will be able to see time as well as amplitude, both these things stored at one place. Now if you want to access this data and if you want to plot the graph, then it is very much easy than the previous method. We'll close this thing and we'll go to any individual variable. So here our variable is 3 signals 3. We'll select the values. When we select it, it will be enabled, and just select the plot. When you select the plot, your data versus time will be directly plotted. Previously we have seen that only the data, that means only the amplitude is plot with respect to points, or only the time is plot with respect to points. But if you want to plot time with amplitude, then you have to do some adjustments, right? But here all the data is stored in one variable, right? Time as well as amplitude. So it is not required to do any line of coding. You just select variable and plot it. Close it, close it. So dataset is a little bit advanced version of storing the data in variable. Now we'll clear all these things We'll go back to simulation. So this is our simulation. Now I'll show you other way to store data to workspace, right? You just need to double click over here and write to workspace. So here we have the block, to workspace block, right? So we'll select this to workspace block with any one signal. When we open it, it will ask us to set the name of the variable. We'll name it as sine wave. The next is limit data point to last. We want to see the full simulation, so here we'll keep infinite only. We'll keep this decimal 1 as it is, but here we have save format. So you will be able to see all these four format that you will be able to see in the scope: structure with time, structure, array, and time series. So basically this time series is the same as data format or data set format in the scope. Let's say we are selecting time series as well. Apply, okay, and let's run this thing. Now let's go to workspace. So in workspace, one signal is our first simulations variable from scope number 1. This 3 signal is from our scope number 2, where we have connected 3 ports, and this sine wave is from that block, to workspace block. The name of that block is to workspace. So we'll open it. We have stored the data in time series format, and in that 3 input scope we have stored all these 3 data in dataset format. So let's open that too. When we open that, we have this multiple set of data, but when we goes to the value, right, we'll be having time as well as amplitude. So here we'll directly have that time as well as amplitude when you use the to workspace block. So you will be able to do all these things which you will be able to do using scope. So using this to workspace block, you will be able to send the data to workspace, which you will be able to do using the scope. All these things you will be able to do using to workspace block. Then the question is, if we can do everything with scope, then why this block is required? The simple answer is, there are various signals which you do not need to observe, and the signals which you do not need to observe, you do not connect scope with it. So when you do not connect a scope, then how can you send the data to workspace? So wherever we are not using scope, and if we want to send the data to workspace, we should go for to workspace block. Because if our simulation is very big, very large simulation, and if we are using multiple scopes, then the simulation will take longer time to run. So instead of using more scope, if you do not want to see all the signals, but you want to have all the signals in your variable in your workspace, so it's better to go for to workspace block rather than going for the scope.
When you are new to Simulink, it's really important to learn how to create sine wave in Simulink, because in every small and big simulation, somewhere we are going to use sine waves, right? So that is why in this video we are going to learn how to create sine wave in Simulink. So first of all, we'll go to library. In library, we'll go to sources. In sources, here we have the block sine wave. Let's add this block, and in sync we have a scope. So let's add this scope too. Let's minimize it and let's connect them together. Now just open it. So when you open this sine wave block, what you will see is sine type, whether you want to go for time base or sample base. So for normal simulations, we'll go for time base.
Hey there, I am thinking to provide two things. First, a free certification MATLAB course, and a second, in-depth structured course with exclusive content, exercise and support which goes beyond what it's available here, and that is paid MATLAB course. So please let me know by commenting or filling out the interest form in description box below whether you are interested in free certification course or in paid course. Thank you so much.
The next is time t, and here also we have two options, use simulation time and use external signal. Most of the time we'll go for use simulation time. And now the important things comes into picture. The first is amplitude. From here you can set the amplitude of your sine wave. For example, I am keeping amplitude as 2. The rest of the things will remain as it is, but just changing the amplitude, running the simulation. So here is the generated sine function. I have provided the amplitude as 2. So what does that amplitude means? That amplitude means the peak value of sine function. And instead of this peak, if you want to go for the RMS, then what you're supposed to do? You're supposed to convert that RMS into peak and then supposed to enter the peak value over here. So if you know RMS of the sine wave and you want to implement a sinusoidal waveform with the RMS that you know, then you're supposed to write the equation in this manner. Let's say your RMS is 70 and you need to multiply it with, so it will convert into peak, right? So let's say okay, close it and now run it. So now you see when the peak is almost 100, the RMS is near about 70, right? So if you know the RMS value, from that RMS you can directly write the peak amplitude of this sine wave. Now the next term is bias. So what does this bias means? Bias means you are providing any external biasing to this waveform. Here the biasing is 0, that means it is not levited either it up or down, right? So the bias is simply the neutral line for this sine wave, and right now that is 0. Now I'll just change amplitude to 10, right? So this is our amplitude. Let's close it. Right, so the amplitude is 10, and now I'm going to change the bias. So right now the bias is at 0, but instead of this 0 I'll make it 2. So the waveform will shifts by 2 steps on upward direction. So let's close it, run it and observe the waveform. So now here you can see the biasing point has changed. The waveform has levitated to 2 volts or 2 steps or any 2 amplitude. Now instead of this plus 2, if you give minus 4, let's run it again, and you can see it's shifted down to minus 4. So by providing this type of biasing, either you can shift the sine wave up or you can pull it down. Now close it. We'll make biasing 0 again, we'll reduce amplitude to 3, right? And now it's time for frequency. Currently the frequency is represented in radian per second. So from this you can set the frequency you want. Let's say you want 10 radian per second, you can set it and run it. So here you can see the frequency has increased. Now let's close it. Now the question is, now here the frequency you're supposed to enter, that is in radian per second. But what if you know the frequency in hertz and directly you want to write the frequency in hertz? Now what you can do, let's say you want to implement the frequency of 50 hertz. So you're supposed to do 50 multiplied by 2 multiplied by pi. So 50 into 2 into pi, that is the frequency in hertz. So the radian per second is nothing but the frequency in hertz multiplied by 2 pi. So okay, run, and here we see the frequency in hertz. When the 50 hertz frequency we apply, a time taken to complete one cycle, that is around 0.02 second, and that's absolutely correct, right? So close it again. Now open here. From the next step you can provide a phase delay, right? For example, instead of 0 radian, you supposed to shift the waveform by 2 radian, right? And let's reduce frequency a bit so that we can have a clear idea. Frequency is 1 radian, phase delay is 0, okay, run. So this is our reference waveform. Now let's make change over here. Phase delay is 2 radian, run again. and you can see the shift in waveform. So by providing that phase delay, you can just shift the waveform. And now finally we have sample time. So what we'll do, we'll make it 0, right? Run. So this is our reference waveform, and the last quantity that we're supposed to understand, that is sample time. Here sample time represents the amount of time after which you will take a sample and plot it in scop. So let's say if I am taking sample time as 0.2, right? So at every 0.2 second it will take a reading and plot. So instead of pure sinusoidal waveform, I'll get this type of steps. So at every 0.2 second it will take a sample. After 0.2 seconds again it will take a sample, and it will create a discrete type of sine wave. So that's how you can create a sinusoidal waveform in MATLAB Simulink.
Hey, if you want to create sawtooth wave like this, or triangular wave like this, or bidirectional triangular wave like this, then this is the video for you. So how to create this type of waveforms in MATLAB in Simulink, that is what we are going to learn in this video. So without wasting time, let's get started. So first of all, we'll go to the library. To create sawtooth wave, you can go to this sources. In sources, this is very useful block, repeating sequence. So add this to our untitled folder, and then to observe the waveform we will use scope. So in sinks we'll go to scope and we'll add it. So here we have two blocks. The first block is of repeating sequence and the second one is scope. We'll connect these two. When you double click it and open, this repeating sequence block will pop up. This is the block parameter of, in first tab you need to enter the time, and in second tab you need to enter the value. Value means the amplitude of your signal. The sawtooth wave looks like this. So to create that waveform, what you need to do, you just need to enter the value of time 0 and 2 represents seconds, and the amplitude we have kept it as 0 and 5. Right, so peak amplitude will be of 5, and again after that it will keep on repeating the sequence. So it will begin with 0 second and maximum around at 2 seconds. Again from the very next instant it will start from 0. So let's make it okay. Run the simulation, and this is how it's look like. If it does not looks appropriate, what you can do, just close this thing, go to simulation, model configuration parameters, and from here you can change the maximum step size and make it to 1e-4. Alright, okay, and run it again. Now you can observe the change in waveform. It looks more appropriate. So it has started with 0, maximum amplitude of 5. From that instant it again goes to 0 and linearly increases up to 5. There are two parameters that you can control. The first parameter is starting point and the ending point, and the second parameter is the magnitude at starting point and the magnitude at ending point. So using these two parameters you can create the sawtooth wave. Now we'll close it.
Hey there, I have provided this complete MATLAB course for free, and I hope it is very helpful and valuable for you. After learning from this course or after completing this course, if you find it valuable for you and if you want to appreciate my efforts, please do consider donating. Your support will help me invest more time and resources into making even better tutorials and provide valuable learning experience for you. You can find the donation link in description box below. So thank you so much for your support.
Instead of sawtooth wave, if you want to create triangular wave, that too you can create using this repeating signal. So just imagine, how does a triangular wave looks like? Here is the picture. So if we want to create triangular wave like this, then we need to define 3 times: the initial point, the middle peak point, and again the ending point. So we'll open it. We'll provide 3 times over here: 0, then 1, and then 2. At 0 second our amplitude will be 0, at 1 second our amplitude will be 5, and again at 2 second our amplitude will be 0. Let's make it okay. Over here you can observe the pattern of waveform on the block appears like a triangular wave. So run it again, open, and this is the triangular wave. So this is how it can generate the triangular wave. Let's close this thing. Now let's suppose we want to generate some different signals. For example, here we are taking all the values in seconds. So instead of this, let's suppose our frequency is predefined, let's say 50 Hertz. So if the frequency is 50 Hertz, the full cycle will end in 0.02 seconds, right? So initial it begins with 0 second and the complete cycle ends in 0.02 seconds. In this time frame, I want to create a bidirectional triangular wave which starts with 0, goes to +1, again to 0, -1, and 0, right? So what I need to do, I need to divide this signal. So first thing I'll do is 0.02 divide by 2. So it will create the center point. Again over here 0.0 divide by 4. So it will create the center point of these 2 points. And over here I will add one more point. So I have created all the points for 50 Hz frequency, and now I'll give the values. For example, it is 0, then it goes to 1, again come back to 0, then -1, and again come back to 0. So the waveform is ready, amplitude I have given. Okay, again you can see it appears that the waveform changes its shape, and you can see the change in waveform, right? Now we'll horizontally expand it. So it begins with 0. How we'll identify it? Well, verify it. We should do it in initial phase. It starts with 0, goes to +1, come back to 0, -1, and again come back to 0. So this sequence will be repeated for the full simulation time. So this is how you can create this type of bi-directional triangular wave too.
Hey, if you want to learn how to generate PWM and SPWM signal into the MATLAB, then this is the video for you. So without wasting time, let's get started. So first we'll take all the necessary components. For that we go to library, and then we go to sources, and in sources we'll take one constant and another one is repeating sequence, right? Then we want to compare both the signals. So for that we'll go to logic bit operation and we'll take one relation operator, and that is here we have that relational operator. And to observe the output we'll take one scope. So now we have all the required components to generate PWM signal. Now we'll understand, using this constant block we can generate a constant signal of any given amplitude. So over here we are going to enter the amplitude. This one is the repeating sequence. Using this block we have to enter two values to generate our required signal. Generally we generate sawtooth wave using this repeating sequence. This indicates the time at particular point, and this will indicate the magnitude at that particular time. So let us assume that for every 1 second we want to generate a pulse, right? So the magnitude over here is 2, which is double than the constant magnitude, right? That is fine. And the third one is repeating sequence. So using this block we are comparing both the signals. So when we want to generate the pulse, when the magnitude of this constant block is higher than the magnitude of this repeating sequence, at that time we want a pulse. So for that we'll select greater than. Okay, and now let's run the circuit. There we go. So here you can see it's our constant, this is the sawtooth wave, and the result of these two is the pulses we are getting.
Hey there, I am thinking to provide two things. First, a free certification MATLAB course, and a second, in depth structured course with exclusive content, exercise, and support which goes beyond what it's available here, and that is paid MATLAB course. So please let me know by commenting or filling out the interest form in description box below whether you are interested in free certification course or in paid course. Thank you so much.
And now let's see all of this three signal in one scope so that we can have a better comparison. So here you can see when the DC signal is higher than this sawtooth wave, we are getting this pulse. And when the magnitude of this DC signal is lower, then we'll get 0 in output. Now if you want to change the width of this pulse, you just need to change the magnitude of DC signal. This is how you can achieve it. Now we are going to generate the SPWM signal, and for that, instead of this constant block, we'll use a sine wave, and we'll compare this sine wave and this sawtooth wave and generate the SPWM signal. So let's just do that thing. So we have got the sine wave block. We'll replace that block. Okay, so now we'll quickly modify a few of the things. We'll open this sine wave, and instead of this 1 radian per second, we'll reduce it to 0.5. And now we'll make few changes in this repeating sequence. We'll make few changes like we'll add 0, 0.5 and 1 second. So at 0.5 second we want the magnitude of 2, and at 1 second again we want it at 0. So every 1 second we'll have a pulse, right? And now we'll run. So here you can see that initially the pulse width is less, and as you approach the peak of the signal, the pulse width increases, and again as you reach at 180-degree, the pulse width reduces. From the center on the left hand side there are two signals, and from this center on the right hand side there are three signals, practically, which is not allowed. So what you need to do is you need to adjust the frequency of this signal and the sine wave in such a manner that you have even distribution of these pulses. I have not looked at about that thing because right now the tutorial is just to show how you can generate this thing. But I'm planning to create an animated video on PWM and SPWM signals, right? So if you are interested in watching those theoretical concepts and importance of the theoretical concepts of PWM and SPWM through animation, just write that thing in comments below, and if I have a good numbers of feedback, I'll definitely make video on that topic. So right now this is how you can generate SPWM signal using sine wave and triangular wave. So now let's close it. Now we'll go for the another method, that is generating pulses using pulse generator. We'll go here and write, and here we have the pulse generator. We'll add the pulse generator. Now when you open this pulse generator, you can see varieties of things. This amplitude represents the peak value of the pulse. The second is period, which defines the time for complete cycle. We'll keep it as 5.
The pulse width defines the amount of time for which the pulse is on. So let's keep it as 50%. So for the 50% of time pulse is on, and for the 50% of time pulse is off. The phase delay will define the delay in pulse. Run it. So from here you can see that the amplitude is 1, the period is 5 seconds. So from here our period of the signal is 5, pulse width is 50%. So the 50% of 5 is 2.5. So for 2.5 second it's on, and for the 2.5 second it's off. And the phase delay, right now we have provided phase delay of 0. Now let us make few changes. Instead of this 50, let's make it 20 and observe the changes. Run and see the difference. Right, so this is what the pulse width creates, and using this block you can generate pulse the way you want.
In this video, we are going to talk about three very useful blocks in MATLAB Simulink, and those blocks are repeating sequence blocks under the sources. So in the sources you will find the repeating sequence interpolated, and repeating sequence stair. So these three are really important blocks in MATLAB Simulink, and in this video we are going to compare each of them and we'll see how they give the output for the same inputs or for the same logic. So first of all, we'll add all of these three. Let's add to untitled MATLAB file. So we have added all these three. The first one is repeating sequence. Let's open it. The repeating sequence block is used to generate the repeating sequence of values. It takes a vector or matrix as input and outputs the value cyclically. This means that once the sequence is completed, it starts again from the beginning and repeat the same sequence. So this is what the purpose of this repeating sequence. Over here you can see there are two parameters. The first is time value, which is horizontal axis, and the second one is output values, which is the magnitude or vertical axis, or you can say y-axis. So here we'll define time. So let's say we are defining time like 0, then 0.2, and then 0.4, and output we want 0, 2 and 0. So kind of a triangular wave we are going to generate using this logic. So now let's close this thing, and now we are going to open the repeating sequence interpolated block. So let's open it. This is the repeating sequence interpolated block. This block is also generate a repeating sequence of values, but it interpolates between the values to provide a smooth transition. It takes a vector or a matrix as input, and instead of direct outputting the values, it interpolates between them using the different interpolation method like linear interpolation or spline interpolation. These interpolation can be useful when you need to create a smooth transition between discrete values. Just imagine that you have a set of data points plotted on a graph like this, but you want to determine the values at a specific location where you do not have any data point. So in that case, the interpolation helps you to approximate the missing values, and this can be done using the surrounding information of the data points available. So this is how it works. Now here also we have two inputs. This is the vector of output values and this is the vector of time values. So here in output values we give the same input as the previous one, 0, 2 and 0, and this one is for the time values, and we'll give the same time values as we have given into the previous one. So let's say it's a 0.2 and then 0.4, right? Then we have lookup methods. Here we have total 4 lookup methods to generate the output, and this is our sample time. So after timestamp of every 0.01 second, it will interpret the values between the two data point. This is the repeating sequence interpolated, and now the third one is repeating sequence stair. Let's open it.
Hey there, I have provided this complete MATLAB course for free, and I hope it is very helpful and valuable for you. After learning from this course or after completing this course, if you find it valuable for you And if you want to appreciate my efforts, please do consider donating. Your support will help me invest more time and resources into making even better tutorials and provide valuable learning experience for you. You can find the donation link in description box below. So thank you so much for your support.
The repeating sequence stair block generates a repeating staircase waveform. It takes a vector or a matrix as input, and the output is given in the form of stair steps pattern. It takes a vector or a matrix as input, and it will give output in the form of stair steps pattern. Each value in the input represents the height of a step, and the duration of each step is determined by the sample time of a block. You can use this type of block when you want to represent a staircase like a signal. For example, in digital control system or any event driven simulation. So here also we'll set the output values as 0, then 2 and then 0. So in all these three blocks we have set the value as 0 to 0 and timestamp is 0, 0.2, 0.4. Here also value is 0 to 0 and the time is 0, 0.2, 0.4, and here also 0, 2 and 0. Now we'll take a scope. First we'll discuss about this repeating sequence interpolated. In this block first I'll tell you how the output changes when we change the lookup method. So for that what we'll do, we'll take 4 blocks. In first block we'll take it as interpolated, then in second block we'll use the use input to nearest, then in third block we'll use input below, and in fourth block we'll use input above. And now what we'll do, we'll just run it for 2 seconds. Let's run. Let me specify name over here so that we can identify it easily. So here you can see these are the 4 methods: interpolation, use AND values, nearest value, below and above. So you can see the result are different from each other, and based on this result you can choose whatever method you want to use. But this is what the difference created in output when you change the method. Now let's close this thing. We'll take another scope over here, and now we'll compare all these 3 repeating sequence block. First, in this case we have compared the lookup methods, and in this case we are going to compare 3 different repeating sequence block. The first one is repeating sequence block, the second one is repeating sequence interpolated, and the third one is repeating sequence stair block. So now let's run this simulation for 2 seconds and let's see what is the difference in the output of each of these 3 block. So let me zoom it. So here you can see this yellow line is for repeating sequence, this blue step line is repeating sequence interpolated, and this step line, the red one, is repeating sequence stair. So that's how you can generate 3 varieties of waveform using the different blocks. So after comparing the output waveform of all these 3 blocks, you will be able to select the block as per your need, right, as per your requirement. When you simply want a repeating sequence type waveform, you can use this repeating sequence block. When you have a scattered data and you want to create a plot in between them, you want to interpret the data, in that case you can go for repeating sequence interpolation. Or whenever you want a stair step type of signals, in that case you can use the repeating sequence stair block.
All blocks available in MATLAB is one type of function block, but it's all pre-configured for a specific function. Now what if you want to add your desired function to MATLAB? So to fill this requirement, here there is a function block in MATLAB Simulink, so that you can code your desired function the way you want. And that is what we are going to learn in today's video. Okay, so now let's first bring all the necessary components. First I'll take a sine wave. And amplitude I'll keep it as 1 only. And then to observe the output, we'll take one scope. So this is our scope, and we'll take two windows, right? Why two? That I'll tell you little later. We'll connect it, and let's before checking the output, let's see the parameters. Amplitude 1, frequency 1. Let's make it 2. For a sake of changing something, let's make it 2. Okay, and now let's run. It is just to observe that what exactly the output of this simple sine wave. So it gives us a simple sine wave in output. And now the real thing comes, that I want to change this sine wave to the square wave like this. And to do this, I want to add my own function to this block. So how to add this thing? We'll go to library, and here you will write function. So there are varieties of functions available, but what we are going to use this MATLAB function, right? So you can double click it to bring, or you can right click it and add to block. So here we have our block. Another way to bring this block, if you remember the name MATLAB function, then delete it, double click it, and bring this MATLAB function Simulink user defined function. So here we have our block. So now the U will be the input, we'll connect it to this side, and Y will be the output, and that we want to observe in the scope, right? So in the scope, we'll observe the output. Now to write the code, you need to double click it, and a separate window will pop up. You will be diverted to the editor toolbox, and here in the script file, you need to write your code. This Y will be the output, and that will be the function of U, which is basically your input. Here you can see that there is only one input and only one output. But instead of having only one input and one output, you can have multiple input and multiple output in this MATLAB function. How to do that thing, that I'll tell you in the next section of this video. But right now, let's jump into the coding of this function. So what we want to do, we want to convert the simple sine wave into the square wave like this. And for that, I'm just writing the code. So this is the simple code we have written, that if the input is greater than 0, Y will be 1, and else if the input is less than 0, Y will be minus 1, and that will give us the square wave of magnitude plus and minus 1. So let's jump to the simulation. So here first we'll run this simulation. And ta-da! This is our output.
Hey there, I am thinking to provide two things. First, a free certification MATLAB course, and a second, in-depth structured course with exclusive content, exercise and support which goes beyond what it's available here. And that is paid MATLAB course. So please let me know by commenting or filling out the interest form in description box below whether you are interested in free certification course or in paid course. Thank you so much.
You can see here the first signal is pure sine wave, and the second one, which is the output of our function. So this is how you can write a simple function in MATLAB. And now I'm going to tell you how you can have a multiple input, multiple output function. For that, now let's add another source. Let's say we have another source, and we'll increase number of port, disconnect it and bring it inside. We'll keep the magnitude and frequency as it is, but we'll give it a phase shift of pi by 2, and these two looks like this, right? So it looks like this. Now what we want to do, that when yellow signal is greater than this blue signal, I want to have a high pulse, and the rest of the time I do not want any pulse, right? So let's do that thing in the function. So let's go to this function. Now here we have two inputs, right? So what we'll do, first change we'll make over here, u, and the another one is v, right? And our output is same y. So now here we'll change the condition. If u is greater than v, then we want y is equal to 1, and else we want y is equal to 0. So if our u signal is greater than the v signal, then only y will be 1. In all other condition, y will be 0. So let's get back to the simulation. Ta-da! Over here you can see there are two inputs, u and v. So we'll connect u with u and v with v, and the y will be output. Let's run. There we go. When the yellow signal is greater than the blue one, the output is high, and in all other condition it is 0. So this is how you can have a multiple input in function. Now let's see how to have a multiple output in function. Close this thing, go to the function, and now we want to have multiple outputs also. So over here we'll make a small change, y comma x. So here we have two outputs, and we'll make it like this. If u is greater than v, x will be -1, right? And in other condition, x will be 0, right? So let's save it and let's jump back to the simulation. Ta-da! Here we have two outputs. Now we need to make some small adjustment into the scope. So now here we have the fourth window, and we'll connect it with this, run it, and there we go. Here we have the another output. The red one is y and the green one is x. And now I'll tell you how you can write one function in another function. Come over here and see, I have already prepared this function. If you don't know how to prepare a function, I have a separate video for that, how you can prepare a user-defined function, right? So in first step, you need to create your own user-defined function. The function which you want to use in this function block, that you need to prepare separately. And how to do that, you can check out my another video for that. So here I have already prepared the function, and the name of this function is sum, right? So what I'll do, instead of this x is equal to -1, I'll write another function over here, and that is sum of u comma v, right? There we go. So now let's run this thing and open it, and you can see that the x is sum of both the signals, right? Yeah, one more thing I'd like to tell you, that sometimes it happens that when you write any user-defined function, you need to save this function in any folder, and when your current working folder is not the same, it will show some error. So what you need to do is, you need to save both these functions into the same folder, so it will not show any error.
This is what we are going to learn in this video. Why do we need Power GUI Block? And when to use this Power GUI Block? So now let's check this out. So guys, here we have the block of the day. The block is Power GUI. So first of all, we'll start with the name of this block. The name of this block itself suggests what and why it is used for. The name is Power GUI. GUI means Graphical User Interface.
So whenever you are dealing with simulation, whenever you are dealing with graphical user interface, at that time you require this block. Don't worry, we are going to explore when and where. And to explain you where exactly this Power GUI block is used, let me explore this library. So in library, first we'll go to SimCaps. In SimCaps, we'll go to Power System. In Power System, we go to this Specialized Technology. And in Specialized Technology, we'll go to Fundamental Blocks. So just expand this Fundamental Blocks. So now here the where part comes. So in your simulation, whenever you are going to use parts from any of this section, then you must use this Power GUI block. And that is why this Power GUI block is located over here. That means in all of these sections, whenever you want to use any of the block, you must use Power GUI block in your simulation. Blocks like different electrical sources, different electrical elements, interface element, machines, measurement units, power electronics devices. Whenever any of this device you are going to use in your simulation, you must use this Power GUI block, right? Let me show you what happens when you use this block and when you do not use this block. So let us switch to my previous simulation, which I have explained in my previous video, 3-phase inverter. So here in this simulation, in this corner, I have used this Power GUI block. So what I'll do, I'll run this simulation. Okay, it's done, and now let's see the result. Okay, so we have the results, right? That means simulation has worked. Now let me remove this Power GUI block. Done. The Power GUI block is not available in this simulation. And now let's run. Oh my god, there are varieties of errors occurs, right? So this happens when you do not use Power GUI block in your simulation, right? So I think first thing is clear to all of you that where should we use this Power GUI block? Whenever we require any of the component from this section of the Simulink library, then we must use Power GUI block. And now the second thing comes, but why we should use this Power GUI block? So let us understand that thing.
Hey there, I have provided this complete MATLAB course for free, and I hope it is very helpful and valuable for you. After learning from this course or after completing this course, if you find it valuable for you and if you want to appreciate my efforts, please do consider donating. Your support will help me invest more time and resources into making even better tutorials and provide valuable learning experience for you. You can find the donation link in description box below. So thank you so much for your support.
Here what you can see, we have different switches, source, load, scope and varieties of things included in this simulation. But now let us understand how exactly the MATLAB functions. The basic, the root of MATLAB is matrix. MATLAB stores each and every data in matrix format, and that I have explained in detail in my first video of introduction to MATLAB. If you are interested in learning that, then this is the video. You can check out this thing later on. So the fundamental of this MATLAB is it's storing all the data in matrix format. But here we are doing everything in GUI format. It is graphical user interface. It's a resistor, right? It's a symbolic representation, or ultimately it's a graphical user interface. But what is happening in backhand? In backhand, each and every component is made up through equations, and you all are aware of this. So each of this block in this simulation is constructed using equations. So how MATLAB deals with this graphical user interface and these equations? There this graphical user interface block comes in picture. So what exactly this block does? This block actually stores the equivalent Simulink circuit that we have prepared in this simulation and stores all the state space equation of that model, and when we run it solves all the equation in backhand and then give the result to the scope, and then we can visualize those results. In other words, it simply stores equivalent circuit of prepared Simulink model in equation form.
right? So make it clear in your mind that the role of this power GUI block is to store all this simulation in equation form, does all the process, and then give it a visual result to us. So this is the role of this GUI block in our simulation. Now let us open this GUI block. When you open it, it has three varieties of solver. Right now it is continuous. You can see it is not enabled right now. I cannot make any change in this. If you want to enable it, what you are required to do, go to simulation, model configuration parameters, and from here I have randomly selecting any of this, right? So once I have selected any of the solver, now open it. So now here you can see the simulation type is enable. There are three types: continuous, discrete and phasor. If you select discrete, then you need to give a specific sampling time, right? This is the time on the basis of what you are discretizing the signal and do the required process. And in the third one, phasor, you are required to give the frequency. We'll make it continuous because I want it to be continuous. Here we have varieties of tools. If you want me to explain all of these things, then write that thing in comment and I'll make a separate video for this, because it requires a long time to explain all these things. You can even make load flow settings over here, right? So that can be also managed from this section. And now the last one is preferences. So these are the different preferences for your simulation: display circuit, differential equation. So these are the different settings and preferences that you can adjust it from here. Even to discuss and explain all these things requires a time, right? The main purpose of this video is to explain you why this power GUI block is used. Both the Demux and Bus Selector blocks are used to extract individual signals from the composite signal. However, there is difference in several things. Things like input requirements and output behavior. In this video, we are going to explore the same thing. So without wasting time, let's get started. So first, let me bring Bus Selector to the blank model file. Bus Selector. So this is how the Bus Selector looks like. And now we are going to import Demux. And this is the Demux. So this is how Bus Selector looks like, and this is how Demux looks like. Now in order to understand the differences between Demux and Bus Selector, what we'll do, we'll take one ready-made simulation that we have made previously in our previous video, where I have explained how to regulate the speed of DC motor, right? So we'll use that simulation and we'll see what is the difference between Demux and Bus Selector. So let's jump to that simulation. Okay, so here we are in the simulation. This is the Demux and this is the Bus Selector. This Demux block is used to separate the composite signal or bus into individual signals like this. This is composite signal and these are the individual signals. Generally it takes a single input signal or a bus and provides multiple output ports, and each port will give a separate signal. The number of output port is determined by the number of signals in input. So this is basically the Demux. Now if we talk about the Bus Selector block is used to extract the specific signal from the bus. It takes a bus signal or a composite signal from the input and allows you to select one or more signal from the bus using signal names or signal indexes. It provides multiple output ports, each port corresponding to the selected signal. The number of output port is determined by the number of selected signal, and this is what the basically Bus Selector is. Now if we go into more detail, there are some key differences between Bus Selector and Demux, and now we'll explore what are the basic differences between them. First, we'll compare the input type. Here we are giving input to Bus Selector and Demux from the measurement port of this motor. Basically, this is the DC motor, the parameter you can see on the display, right? So this is the measurement port of this DC motor, and there are multiple signals generated in this measurement port,
and both this Demux and Bus Selector are transferring those multiple signals and converting into individual signals. Now we'll compare this Demux and Bus Selector using the type of input we give to both these blocks.
Hey there, I am thinking to provide two things. First, a free certification MATLAB course, and a second, in-depth structured course with exclusive content, exercise and support which goes beyond what it's available here, and that is paid MATLAB course. So please let me know by commenting or filling out the interest form in description box below whether you are interested in free certification course or in paid course. Thank you so much.
First we'll see this Demux. Basically Demux block accepts single signal or bus signal. Here we are giving multiple signals, right? A composite signal or a bus signal. Whereas this Bus Selector accepts bus signals. It requires multiple signals in input. So basically let me tell you what is the difference between single signal and bus signal. Basically single signal in Simulink represents scalar value or a vector value. It is simply one-dimensional data signal that carries single value or sequence of values over the time. Single signals are often used to represent variables such as sensor reading, control signals, or intermediary calculations within the model. Now if we talk about the bus signals, a bus signal is known as a bus object or a bus. It composite data structure that can hold multiple signals or the value of different types. So this is the key difference between single signal and a bus signal. Now if we compare both this Bus Selector and Demux for its output ports, right? So basically the Demux block provide multiple output ports, and those output ports you can see over here. And by double clicking it, you can control the number of output port you want. And this Demux automatically separates the input into individual signals and give it us in output. Now if we talk about Bus Selector, it is also provide multiple output ports, but the number of output port is determined by the number of selected signals. If you double click it, you will be able to see these are the numbers of signals that is available into the input of Bus Selector. Now we'll just remove all the signals, right? And you can add whichever signal you want to see in output. You can select any one of these four, you can select two, or you can select all of them. You can even arrange the sequence of the signals. If you want to bring it up, you can bring it up, or if you want to bring it down, you can bring it down. So this type of customization is available with the Bus Selector, which is not possible with the Demux. Here in Demux, you do not need to explicitly specify which signal to extract. It automatically separates input signals and give it to you. Whereas in Bus Selector, you need to select which signal you want to extract, in which sequence you want to arrange them, and then you will get the output. One more important key difference is output signal name. When you are using Bus Selector, the output port are automatically named based on the selected signals from the bus. Each output port is labeled with the name of corresponding selected signals. Whereas if we talk about Demux, in Demux, the ready-made signal name is not available. What you're supposed to do, you're supposed to click it, right click it, go to the properties, and over here in signal name, you're supposed to enter the name of the signal. So when you run this simulation, when you open the scope which is connected to Demux, you cannot see any signal labeled over here. Whereas in Bus Selector, you will be able to see the labeling of the signals. There are few more small differences are there in between these two, but I think for regular work, this much of information is enough. If you want to know more, then write that thing in comments below. And if you want to explore similar interesting tutorials on Simulink, just jump to this playlist and explore Simulink. And if you want to go for entire MATLAB tutorials, then you can jump over here. So see you in next video.
Just imagine you are designing a temperature control system for a greenhouse. You can use if-else logic to switch between heating and cooling modes based on the current temperature. Isn't it wonderful? Or
When modeling a battery charging system, you can use if-else logic to control the charging process. If the battery voltage is below the set value, the charger initiates the charging. Otherwise, it stops the charging process. Or when simulating a home automation system, if-else logic can be used to control various devices based on the user input or sensor reading. For instance, if a motion sensor detects a movement, the system turns on the lights. So these are few examples where you can use if-else logic in Simulink. But the most important thing is how to implement if-else logic in Simulink. So that is what we are going to do in this video. So without wasting time, let's get started. Let's imagine we are building a smart temperature control system where we are going to implement and learn how to use if-else logic in Simulink. For that purpose, here I have imported data like wind speed, temperature, humidity and solar irradiance. And all this data I am importing from a weather station. And we are going to use this data to make decisions using if-else logic. But before moving ahead, it's important you know how to import data to Simulink. If you know how to import data, that's fine, move ahead. But if you don't know how to import data to Simulink, then I refer you to watch one video on how to import data to Simulink, which is really very useful tutorial. The link of that video is in description and above here in I button. So refer this video to learn how to import data to Simulink. And now let's build a logic circuit. So first let me show you what are the data that I am importing. This is the scope and I am connecting this data with scope. So let's just run this thing to observe what are the data that we are extracting from weather station. So these are the data which we have imported from weather station. Now using this data we are going to create a logic. Now what is the condition that we are going to implement? The condition is if temperature is greater than 28 degrees centigrade, we supposed to turn on the cooling system. Let's say we supposed to turn on a fan, right? So this is the graph of temperature. So when this temperature is greater than 28 degree, we supposed to turn on the fan, and when it is again below 28 degree, we supposed to turn off the fan. So this is what we want to implement in this circuit. So let's close it. Let's open library. In library, we'll go to signal routing. In signal routing, we are going to use the switch. Let's add the switch. Now just open the switch. Now in the switch, this is the criteria for passing the first input. So this U2 is our input. And here we can set a varieties of criteria if U2 is greater than or equal to threshold, if U2 is greater than threshold, or if U2 is almost equal to 0. So let's say our requirement is if temperature is greater than 28 degrees, so we'll use this U2 greater than threshold and we'll set our threshold to 28 degree, right? Okay. So now we have set the threshold limit to 28 degree. So now U2 is our temperature. So let's connect this to our temperature. So this temperature's reading is given to this switch. And now we can set two conditions. So in order to set the conditions, if input is greater than 28 degree, the upper input is reflected in output, or if the input is less than 28 degree, the lower input is reflected in output. So in order to turn on something, let's say we'll give a constant. So we'll use a constant block and we'll give the magnitude as 1. We'll take another constant block, give it over here, and we'll make it 0. So the logic is set in this manner. If this temperature which is given to this switch, if this temperature is greater than the threshold that we have set, which is 28, so if temperature is greater than 28, this 1 will be reflected in output, or if it is not greater than 28, this 0 will be reflected in output. So let's use a scope to observe the output, and let's connect this temperature with the scope so that we can compare the variation in temperature with the output. Now let's run.
And here you can see when the temperature is increasing this 28-degree mark, the output is shifted from 0 to 1. And again when it is reducing its magnitude from 28 degree, the output is again 0. So that's how this logic functions. Now I'll give you a little bit more complex logic to implement. But before that, I would like to ask you, are you enjoying this simulation journey so far? Don't forget to hit the like button if you found this video helpful. And if you want to stay updated with more exciting Simulink tutorials, make sure to subscribe to this channel. And now we have the more complex new condition, and the new condition is, what if we need to turn on the fan when temperature is higher than 28 degree and solar irradiance is greater than 30 watt per meter square? So this is our new condition. So here we have two conditions: temperature is higher than 28 degree and solar irradiance is greater than 30 watt per meter square. So now let's open this scope, and here the solar irradiance is this green one, right? So first we'll connect the solar irradiance in this scope. Now I'll take one more switch. Now I'll open this switch, and in this switch I'll set the threshold of 30 watt per meter square. So this is my first logic. If the solar irradiance is greater than 30 and wind speed is greater than 28, then and only then the output will be 1, right? So I'll give the input from solar irradiance. So this is my input. Now first I'll take a constant block with 0 magnitude and connect over here, and then I'll connect a constant block with 1 magnitude and connect over here. Now what I'll do, I'll connect the output of this block to this upper section. So let's remove this line and connect it over here. Now what will happen in this logic, let me explain quickly. So let's say when temperature is greater than 28 degree but solar irradiance is less than 30 degree. So what will happen, this 0 is reflected in output and the same 0 is reflected over here. So the input to this logic is 0, and when the temperature is greater than 28 degree, the upper logic is connected in output and the upper logic is still 0. So our main output will still remain 0. So cooling system will not be turned on. Now let's say it is less than 28 but solar irradiance is greater than 30. So when solar irradiance is greater than 30, one output will be reflected over here, but temperature is less than 28. So what it does, it will take lower output and reflect this 0 input in output. So in both the case our condition is get fulfilled. Only and only when the solar irradiance is greater than 30 and wind speed is greater than 28, in only that condition the output will be 1. Let's run and observe. See, here you can see solar irradiance is greater than 30 in between these 2 points and temperature is greater than 28 degree in between these 2 points. So what is the common time when both the logics are true? The common time is this much only. And you can see the output is 1 for only that much of period of time. So that's how you can implement if-else logic in Simulink.
Hey there, I am thinking to provide two things. First, a free certification MATLAB course, and a second, in-depth structured course with exclusive content, exercise and support which goes beyond what it's available here, and that is paid MATLAB course. So please let me know by commenting or filling out the interest form in description box below whether you are interested in free certification course or in paid course. Thank you so much. Hey, in this video we'll learn how to prepare the full bridge controlled rectifier in Simulink, as well as we are going to discuss the result. I'll also share some of the tips through which you can also speed up your simulation and analysis. So without wasting time, let's get started. So to prepare the circuit, we'll go to library, and in library we'll go to SimCaps. Here it is. In SimCaps we'll go to power system, and in that power system specialized technology, and in specialized technology the fundamental blocks. Here in the fundamental blocks, electrical sources, and we'll start with AC voltage source. We'll add it, then we'll add the load. We'll use RLC branch. Then we want some power electronics device, so we'll go to power electronics. Here we have varieties of device: idle switch, IGBT with diode, MOSFET, GTO, Thyristor, and a ready-made full bridge converter, right? But we are going to use this Thyristor. Full bridge rectifier is a simple circuit, and creating it by yourself, it gives you a detailed idea. So I suggest that whenever you are going to prepare a simple circuit, do not use ready-made bridge. Create it by yourself so that you can have in-depth idea. So here we have all the components. Just click Control and drag it. It will duplicate this device. Control plus R, it will rotate it by 90 degrees. So power circuit is almost ready. Now we are going to provide the gate pulse. To provide the gate pulse, we are going to use the pulse generator. Double click it and write pulse generator. If you want to learn how to use pulse generator properly, then I have created a separate video. You can watch that video and learn how to use pulse generator in detail. Period would be 1/50, pulse width 5% enough, and phase delay would be A into 0.02 divided by 360. Now our entire circuit is ready. Gate pulse of switch S1 and S4 are same, and gate pulse of switch S3 and S2 are same. Why it is like this, I will explain it little later. Now exactly what are the results that we want to observe? Basically we are interested in observing the input supply voltage and the output voltage. So what we can do, just double click it and in measurements select voltage. Okay. In load, branch voltage, branch current, voltage and current. So these are the different parameters you can measure. Right now we are interested in only voltage, so we'll select branch voltage. Okay. Now we are going to set the supply parameter, the peak amplitude of the voltage. If we want to keep 220 volt RMS, around 320 volt would be the peak magnitude. Phase delay 0, frequency 50 Hz. That's it. So almost everything is ready. Now we are required to add the thing in which we can observe the output. So first we have measured the output, and now we are going to use multimeter. This is our multimeter. Using this multimeter, without any wire connection, we can get the signals from the source and load to this multimeter, and through this multimeter we'll see the signals in scope. So we require one scope. So we'll add one scope. If you want to quickly add the device, what you're supposed to do, just double click it. So this window will pop up, and here you need to write the name of the device. For example, I want to add scope, so I'll write scope, and there we go, we have the scope, right? So this is more quick and easy way to add the devices. But if you are beginner, may be possible that you do not remember the name of the devices. For that you need to go to the library browser, and in this sources and sync you can get all the important components. And if you don't know that, then you can search it from here. So now just double click this multimeter. The first error multimeter show is this. So we'll remove this error. This error is because here we have provided a plus 180 and a. So we have not defined the a, and that is why this error is popping up. One more error will come because we have not used one block. We have intentionally not kept that block in our system right now. So first let's add the value of a and then we'll proceed. So here, for example, we want to add a is equal to 60 degree, right? So our firing pulse would be at 60 degree. Now again it shows the error, and this time this is because we have not added the power GUI block. Why we require power GUI block? In depth, in detail video of the power GUI block, around 4 minutes of video I have created on the power GUI block, that why it is required, what is the need of power GUI block. I insist, if you are working with Simulink, you must watch that video. Right now here I am directly adding power GUI block. So here we go, we have this power GUI block. Now there we go, we have no error. So first we'll select this voltage source, we'll get it on right hand side, and then the R load close. So we have two signals and now we are ready to run. But before that we'll reduce the time of this simulation, and now let's run. So this is our simulation. So this yellow is the input supply and the blue one is the output of the full controlled rectifier. And now it is the time I will tell you why I have kept the gate pulse of switch S1 and switch S4 same, whereas switch S3 and switch S2 are same. The reason behind this is, in positive half cycle the time would be from 0 to 0.01 second. In this duration, this terminal of supply is plus and this one is minus, and because of this the current flows in this direction, and the full path would be like this. So because of this, these are the two switches S1 and S4 which can control the output, and that is why the gate pulse of switch 1 and switch S4 are the same. Whereas in negative half cycle the time duration is from 0.01 to 0.02 or 180 to 360 degree. In this period this terminal is positive, this terminal is negative, and current flows through this direction. So in this period the switch S3 and switch S2 can control the output, and that is why the gate pulse of switch S3 and switch S4 are the same. Now the important thing is, now it's time to understand that why for switch S1 and switch S4 the equation is like this, and for switch S3 and switch S2 the equation is like this. The minor differences of this additional 180 in switch S3 and switch S2. The reason behind this is, switch S1 and switch S4 are going to be triggered in between 0 to 180 degree. For example, if we are triggering the SCR1 and SCR4 at 40 degree, then we supposed to trigger SCR3 and SCR2 at 180 plus 40 degree. So in order to maintain the half wave symmetry, we supposed to trigger the SCR3 SCR2 at a plus 180 degree, and this is the reason why I have added this 180 degree in this equation. So it will help in maintain the half wave symmetry. But why we supposed to maintain the half wave symmetry? This half wave symmetry will help in to reduce the input side harmonics. If you are not too deep into this analysis of harmonics, then forget about this. But if you are really concerned about the harmonics, then this is really important. So I think it's clear to you that why it is like this. And now it's time to observe the waveform with RL load, and then you will be able to understand that what is the effect of inductance of load on the output of rectifier. See what's happening previously.
When the load is just pure resistive load at exact 180 degree, switch S1 and switch S4 are turning off because the load is purely resistive. But now when the load is RL type, resistive plus inductive, so at exactly 180 degree, this switch tries to turn off, but because of this inductance, current suddenly cannot change its direction, and that is why the current flowing through both these devices is not reducing to zero, right? Current reduced to zero after several time, and once current reduces to zero, this devices gets turned off. So for this much of time, current flows in the same direction, but because the supply voltage changes its direction after 180 degree, the voltage applied on the load would be negative. But at the same time, current flowing through the load is still the same as previous in this direction. So this is what happens when RL type of load is connected with the rectifier. Hey, in this video we are going to prepare a 3-phase controlled rectifier. So let's start with the blank canvas. First of all, we're supposed to bring a AC voltage source, and for that we'll go to library, and in library sim caps, in that power system, in that specialized technology, and in that we have varieties of sections, and in these varieties of sections we'll go to electrical sources. Here it is. So in electrical sources we'll bring controlled voltage source, we'll take a 3-phase source. You can directly take a single phase source and make it to 3-phase source, but here in this video I am taking a 3-phase source. And then we'll go to elements and we'll take series RLC branch. Once we get that, then we'll move towards the power electronics device that we want to use for this, and that is Thyristor. We'll use Thyristor. Once we have that, then we'll go to measurement block, and from here we'll use one multimeter, and then we'll have a 3-phase measurement block, and finally we'll go for scope. So we'll add scope. So I think majority of the things we have got here. Now we just need to arrange it in appropriate manner. So now I am going to prepare the circuit, so you just observe it. Okay, so our circuit is almost ready, and now we are going to add a power GUI block. This block is really very important for simulation, and you always need to use this power GUI block. If you want to know that what exactly the requirement of this power GUI block, then you can refer my another video. Now we are going to generate pulses for all the 6 switches, and for that we are going to use pulse generator. So let's get it. So this is our pulse generator.
Hey there, I am thinking to provide 2 things. First, a free certification MATLAB course, and a second, in-depth structured course with exclusive content, exercise and support which goes beyond what it's available here, and that is paid MATLAB course. So please let me know by commenting or filling out the interest form in description box below whether you are interested in free certification course or in paid course. Thank you so much.
Now in order to generate the pulses for all these 6 switches, what is the exact sequence in which you are required to generate the pulse? So for example, if we are taking pulse at 0 degree, then switch 1 we will fire at 0 degree, switch 6 after 60 degree, switch 3 after 60 degree, switch 2 after 60 degree,
switch 5 after 60 degree and switch 4 after 60 degree. So there are total 360 degree in one cycle and we have 6 switches. So 360 divided by 6 switches, so we'll get a gap of 60 degree. So after every 60 degree we'll fire the switch, but the switching sequence would be like this: T1, T6, T3, T2, T5 and T4. So now let me arrange the pulse generator for all the 6 switches. First we'll start with this. Amplitude 1, time period would be 0.02 second. Pulse width is 5%, this much is enough. If you want to go for 10%, that much is also enough. And now here I am going to write the equation to convert the phase delay seconds into the degree, right? So A into 0.02 divided by 360. So this is the equation. So after S1 we are supposed to go for switch number 6. So we'll name it as S6. Let's connect it. But what is the sequence? We supposed to turn it on after 60 degrees. So this is A is our firing angle. So what we'll do, we'll add 60 degree to it, right? After switch 6 we should go for switch 3, that is after 60 degree. So after 60 degrees 120, then we should go for switch S2. So that is after 60 degree, so that is 180 degree. And here you will get one verification check, that is the switch S1 we are starting at 0 degree, right? It is at 0 degree. And switch S2 we are starting at 180 degree, right? So switch S2 we are turning on at 180 degree. So it should be a gap of 180 degree in single lag, because if we turn on switch 2 device before 180 degree, what will happen? There is a possibility to get a short circuit in between this lag. So at least a gap of 180 degree should be maintained between the two switches of same lag. Now after S2 we'll go for S5, right? And we'll add another 60 degree to it. So after 180 it should be 240, and after S5 we should go for S4. So for S4 we'll add the gap of another 60 degree, so it will become 300 degree, right? So I think gate pulse of all the switches is ready, and now we are supposed to go for measurement of voltage and current. So here we'll take a branch voltage, right? We want to measure branch voltage. Okay, this shows the error. The error is nothing but we have not provided the gate pulse here, right? Because A is still unknown, and that is why that error is shown. So let us define A here. Let us say A is equal to 0 degree, right? Now we have defined A. Now there is no issue here. R load, we'll take it and close. So we are measuring R load, and now we'll start measuring a 3-phase voltage, right? You can directly bring and add another signal to the scope. You are not supposed to go and add another signal into the scope. So now we'll open the scope, and if we want to change the view pattern, then we can set the layout is like this, right? So in top we'll get 3-phase supply voltage, and in another section we'll get the output voltage. Now we'll adjust the time. I think for 0.1 second time it's enough. We'll save this file. So 3-phase control rectifier is the name of our file. Now let's run. Oh my god, the output is very weird. This is because we have not set any parameter for the source. We have did all the calculation for 50 Hz, right? Gate pulse sequence we have arranged for 50 Hz, and here it is 60 Hz. So that is the problem. And now let's say phase to phase voltage, we will keep it as 415, and we do not want any internal impedance. Let's go again, and there we go. That's right. So these are the three phase voltages, and this is our output, a DC output. Now you can even measure the supply current as well as the load current using this branch current, branch voltage and branch current.
Okay, so first we'll start with circuit making. We'll go to library. So here we have all the necessary components to prepare a power circuit of inverter, a single phase inverter. So now let me connect the circuit. So here our power circuit is ready. Supply voltage is 100 volt and load is of 50 ohm. Now in first method we'll give simply square wave like this using pulse generator. So let's prepare circuit for that. We'll use pulse generator. We'll open it. Amplitude will be 1, period will be 0.02 second, pulse width would be 50%. That means for 50% of this much of time it will be on, and for the 50% it will be off. So it will be on for 0.01 second and it will be off for 0.01 second. Okay, so this is PG1 and we'll connect this PG1 with the switch S1. Now we'll duplicate it. It will be PG2 and that will be for switch number 2. In inverter, the two cross leg switches are working together, switch 1 and switch 3 for positive half cycle and switch 2 and switch 4 for the negative half cycle. So using this pulse generator 2, we'll be producing pulses for switch number 2 and 4. We'll open it. Period and rest of the things will remain same, but delay will be 0.01 second. Now using this from block, we'll take input directly from this pulse generator. Now we'll tag this as switch number 1. You can give any tag as of your choice, but here I am giving all the tag as switch number, and here we should give it as. So here we have given S1, S2. We'll take two more go to blocks. So here we have all the 4 blocks ready. Our pulse generator is ready. We'll reduce the operation time, simulation time, save it, and now before running we'll take one power GUI block. This power GUI block is always important while we doing any simulation in SimCaps. Even to observe both these pulses, we'll take one scope over here. Now let's run the simulation. We'll make it so now you can see for positive half this is working, and for negative half the another switch is working. And let's see the output of inverter. So here you can see the yellow waveform is of current and the blue waveform is of voltage. So it is alternating in nature and converting DC into AC. Now let's suppose instead of this type of full square wave signal to this inverter, what if we can give a PWM signal to this inverter? So how to give this type of PWM signal to this inverter, we'll see in this section. So now we'll prepare a control circuit which produces PWM signal for this inverter. We'll add this constant block, then we'll add a repeating sequence, and to compare both of these signals we want a relational operator, and finally to have, you know, signal for particular time, we'll add a logical operator. We want to have scope. So now we have almost all the components to produce PWM signal. So now I'm going to prepare circuit for that. So now here our circuit is ready. In this constant block we are giving a constant magnitude of 1, and in this repeating sequence we are going to generate a triangular wave of magnitude 2. These are the time values to provide a 20 triangular signal in 0.02 second. Why I did this, I'll tell you later on. So using this combination, I'm going to compare this constant block with this triangular and going to produce a pulses. Let's see that thing. So here I have pulses. I am comparing this triangular wave with this constant signal and getting this type of pulses. But here the question is, all these pulses are constant. But what I want to have pulses for these two switches from 0 to 0.01 second, and pulses for these two switches from 0.01 to 0.02 second. So in order to achieve that thing, we'll use these two pulse generators. Pulse generator 3, what we'll do, we'll compare these pulses with this PWM signal to get output in only and only positive half cycle. So let me show you that thing. So now you can see here that we are getting pulses for 0 to 0.01 second, and for the other half cycle we are not getting any pulses. The same way to produce signals for S2 and S4 switch, what we'll do,
Hey there, I have provided this complete MATLAB course for free, and I hope it is very helpful and valuable for you. After learning from this course or after completing this course, if you find it valuable for you and if you want to appreciate my efforts, please do consider donating. Your support will help me invest more time and resources into making even better tutorials and provide valuable learning experience for you. You can find the donation link in description box below. So thank you so much for your support.
we'll take this pulses and compare it with this PWM signal. So here you can see we are getting pulses for positive half cycle and pulses for negative half cycle. So we have updated from and go to port names, and now let's run the circuit. So these are the pulses for the switch. Now we'll see the output of inverter. So here you can see the pulses in output voltage as well as current. The blue one is output voltage and the yellow one is output current. So this is how you can produce PWM output in inverter. Now here, just by controlling the magnitude of this constant block, you can adjust the width of the pulses. Now just imagine, what if you want to produce SPWM signal instead of this type of PWM signals. So to achieve SPWM signals like this, let's prepare the control circuit. Sources will take sine wave, will take repeating sequence, We'll take scope relational operator. So using these blocks, now I'm going to prepare a control logic to produce SPWM signal. In the sine wave block, the amplitude is 1 and the frequency is 2 pi 50 radian per second. That will give us a 50 Hz cycle of sine wave. Now the next thing is repeating sequence block, and here the same block I have used which we have used earlier. The second is comparator block, and here I have added two go to block and I have updated the name as SSS1 and SSS3. Now I will replicate the same circuit to produce SPWM pulses for S2 and S4 switch. Here in sine wave block, what we need to do, we need to provide a delay of 180 degree. So to create that delay, we'll write it as pi. Pi means 180 degree. So here we have provided 180 degree of phase delay. Now we'll update these names SSS2. The same thing I will update over here also. So I have updated all the from blocks and all the go to blocks. Now let's run the circuit. And first we'll check this. So here for first cycle you can see we are getting SPWM pulses. The width at the beginning is very less, and as we approach to the center part of the signal the width will increase. So this is the SPWM signals we are getting for positive half cycle, and here are the another SPWM signals that we get for negative half cycle. So these are the signals for negative half cycle. And now we'll see the output of inverter. So here is the output. So this is the voltage waveform and the yellow one will be the current waveform. So this is how, using these three methods, you can generate pulses for the inverter. If you have really enjoyed this tutorial, then hit thumbs up button to this video and appreciate my work. So here we have necessary components to prepare the circuit. Now just observe how I am preparing the circuit. First I will prepare the power circuit of 3-phase inverter. Now the hardware circuit is ready. Now I am going to integrate the 3-phase load with this 3-phase inverter as well as the measurement instruments with this load. Here our circuit is completely ready, but now I am going to connect the scope to observe the voltage and current of this 3-phase inverter. So here we have three scope arrangement for line current, line voltage and phase voltage. So now I'll give proper tagging for this go to block and from block. Okay, so now everything is ready and we are ready to implement the first technique, where we are going to implement a square pulses like this to this 3-phase inverter using the pulse generator. So let's prepare the circuit for that and then implement over here. For that we require only pulse generator. Period will be 0.02 second, pulse width would be 50%, and there we go. Here we are ready with our first pulse generator. Now in order to operate this 3-phase inverter, we require to operate all these 6 switches in several patterns. For this video, we are going to operate this inverter in 180 degree mode of operation, and for that the pattern will be like this. First we operate switch number 1, then 6, then 3, 2, 5 and 4. In different videos and in different book, you find different numbers of switches placed at different location. But the fundamental logic and principle remains the same. To simplify this thing, you need to remember this specially designed X. 1, 6, 3, 2, 5, 4. This will help you to remember the switching sequence of this three-phase inverter. So as per this logic, what we're supposed to do, we're supposed to operate the switch number 1 at 0 degree, switch number 6 after 60 degree, then switch number 3 after 60 degree, 2 after 60 degree. So likewise, the switching angle for all these 6 switches will be like this. So as per the previously mentioned switching sequences, this PG1 will be given to switch number 1. So let me arrange go to and from block for this switch and pulse generator. So here we are ready with all the gate pulses from switch number 1 to switch number 6. So here switch 1, 3 and 5, these are the 3 switches of the upper section, and switch 6, 2 and 4 are the switches of lower section. Now we'll add one power GUI block. So whatever we need to prepare, we have prepared everything, and now it is time to provide a proper sequence to all the 6 pulse generators. So as per the gate pulse sequences, this pulse should start at 0 degree, and then this PG6 should start after 60 degree. So let's arrange it after 60 degree. So this will give the delay of 60 degree. Then the next gate pulse is PG3, and that is on 120 degree. Likewise, I will set time delay for all the other pulse generators. So now everything is set and we are about to run the simulation. Instead of this much small time, I'll make it 1 second, and then let's run the simulation. So first let's see all the gate pulses. So here you can see that these are the 6 gate pulses for this 3-phase inverter. And now we'll go for the phase voltage. So here you can see the 3-phase voltage. So here is the VR, VY and VB 3-phase voltages. Now let's see the line voltage. So here in line voltage you can see there are 2 steps, and in phase voltage you can see there are 3 steps. Now let's observe the current, and this is the output of current. So this is how this 3-phase inverter with 180 degree mode of operation can be done. You can even operate this 3-phase inverter with 120 degree mode of operation, with 150 degree mode of operation, and if you want to achieve those things, then you need to do slight arrangements in all this pulse generator. If you want a separate video on 120 and 150 degree mode of operation, then write in comments below, and if I get handfuls of comment, I'll make video on that topic. Now after implementing this simple square wave with this 3-phase inverter, now it is time to go for the second method, and in this method we are going to implement the pulse width modulated signal to this 3-phase inverter. So here we'll produce PWM signal for all the 6 switches. So in order to generate PWM signals, we required several things. So let's gather those things. So these are the components that we require to produce a PWM signal. So how we'll produce these PWM signals? We compare a constant DC signal with the triangular wave, and then we compare both this wave. So when the magnitude of DC signal is higher than the magnitude of triangular wave, at that time we will get the output pulse. And this is how we are going to get the PWM signals. So now here let me arrange the circuit for this. Here the magnitude of constant block will be 1 and here the magnitude of this time value will be like this. This time value means we want a 20 triangular into the period of 0.02 second, and the peak magnitude will be 2. The result of this will be the PWM signals. Let us check this thing. So here you can see that we are getting the pulses. But let me tell you, whatever pulses we are getting at the output of these two blocks comparison, the pulses are continuous pulse. But what do we want? We want pulses in specific sequence for all the 6 switches. So in order to achieve all the pulses in specific sequence, what we are going to do? We are going to have AND operation between each of this pulse generator and the continuous pulse. So finally, as a result, what we get? We'll get PWM signal for that specific time. Let me have a logical operator here. So what we'll do? We'll do AND operation. The first will be this pulses and the second will be the output of this pulse generator 1, and that will be this. And now you can observe over here that we are getting pulses for specific time. Here it is continuous pulse, but here we are getting pulses for specific time. So likewise, I will generate pulses for all the 6 switches. Now here complete setup is ready. So now the tag you can see over here, that should be same as the tag at the gate pulse of the switch. So now I will update all these tags. So here all the tags have been updated, and now let's run the circuit. First let's observe the gate pulses. So here are the gate pulses for different switch. The first one is the continuous pulses and the second and third is the pulses for different switch. And now let's see the phase voltage. So this is how you can get the phase voltage of all the 3 phases R, Y and B. Now let's observe the line voltage. So these are the line voltage of VRY, YB and BR. And finally we'll go for the current, and this is the current of all these 3 phases. So this is how you can generate the PWM signal for 3-phase inverter. Now just imagine, instead of this pulse width modulation technique, what if you can implement the sine pulse width modulation? That will improve the output of 3-phase inverter. So in order to achieve improved output, we used to have sine pulse width modulation technique. So now we are going to implement the third sine PWM technique for this 3-phase inverter.
Hey there, I am thinking to provide 2 things. First, a free certification MATLAB course, and a second, in-depth structured course with exclusive content, exercise and support which goes beyond what it's available here, and that is paid MATLAB course. So please let me know by commenting or filling out the interest form in description box below whether you are interested in free certification course or in paid course. Thank you so much.
Now we'll gather all the components. So here we have got all the necessary components. What we are going to achieve over here, we are going to compare this sinusoidal wave with the triangular wave, and the result of these two comparison will get a sine PWM pulses like this in the output. So here, in order to achieve appropriate SPWM signal for all the 6 switches, we require a separate 6 sine sources for all the switches, and all these sine sources should be 60° apart from each other, and then we compare everything with the triangular wave. So now I am going to prepare a circuit for that. So here the complete circuit is ready. So we have 6 sine sources. The first source parameter are like this. Amplitude we have kept as 1, frequency is set at 50 and the phase delay is 0. The next is for switch number 6. And over there we have provided the delay of 60 seconds. Then the phase delay of 120°. and likewise in all the switches. So finally in the last switch the delay will be of 300 degree. And then we are comparing it with a triangular wave with the similar pattern that we have used in PWM signal. So here what we are doing, here we are creating 20 triangular signal in time of 0.02 second with the peak magnitude of 2, and the output is given to the go to blocks. And over here the from block we need to update the tag. So here we have updated the tags, and now let's run the circuit. So first we'll observe the SPWM signals. So this is how the SPWM signal for all the 6 switches looks like. Now let's see the phase voltage. So from this picture you can see that the output looks more sinusoidal. So this is the output of phase voltage. Now let's observe the line voltage. It's the output of line voltage. And now let's see the current. And here it is, the current of all the 3 phases. So here by observing all these waveforms of line voltage, phase voltage and phase current, you can conclude that the output of this 3-phase inverter is better when we use SPWM signals. Okay, so in this video we are going to learn how to implement or how to utilize the 3-phase programmable voltage source in MATLAB Simulink. So first let's get the voltage source, and for that we'll go to this library. In library we'll go to SimCaps. In SimCaps we'll go to power system, and in power system we'll go to specialized technology. In specialized technology we will go to fundamental blocks, and in fundamental blocks we'll go to electrical sources, and in electrical sources here we have 3-phase programmable voltage source. Let's add this. So here we have 3-phase programmable voltage source. Now we'll take one load resistance. So let's add 3-phase RLC branch. So here we have 3-phase series RLC branch. Double click it. We'll take only resistance and we'll make it 100 ohm. That's it. Okay, so we have connected this source to the resistance. Here we have a scope. Now we'll take a voltage measurement. So here we have a voltage measurement block. Basically we want to measure the phase voltage of these 3 lines. So what we'll do, we'll connect a positive to this line and the negative to neutral, and that's how we'll be able to measure the phase voltage. We'll do the same thing for another line. So here we have created the entire circuit. In this circuit, this is our supply side, this is the load side, this is our neutral. Using these 3 voltage measurement units we are going to measure the voltage, and using this scope we are going to observe the waveform. Now it's time to understand 3-phase programmable voltage source. What is inside this source? So first thing we will be able to get is positive sequence. In here we are supposed to add the amplitude, which is basically the RMS voltage, which is phase to phase. Then we are supposed to add the phase or the degree by which your first phase will delay, and the third one is frequency. So let's say we are keeping the amplitude 100 as it is. We are going to change the frequency, which is 50. Let's make it OK, and now let's run. But before running I would like to tell you that we have still missing one block. We're supposed to add one block in this simulation, and then we're supposed to run. But first let's see what happens if without that specific block if we run the simulation. Now let's run. So when without that specific block if we run the simulation, it will create an error. And what is that block? That block is this power GUI block. Let's close it. Let's add that power GUI block. Here it is, power GUI block. Now we have that power GUI block, and now let's run the simulation.
and it's completely fine, right? So power GUI block is needed when we do the simulation. But what is the need of this power GUI block? And if you want to understand the exact requirement of this power GUI block, I have created a separate video for that. The link is in description and above here in card, so you can refer that video a little later. Right now let's open this thing and observe the waveform. We'll make it horizontal zoom. Here you can see we have given the amplitude VRMS phase to phase, which is 100 degree, but over here you can see that the peak is 80, so the RMS is much less than that. But let me tell you that this quantity is phase to phase, or we can call it as a line voltage, right? So the line voltage is 100 volt, and what we are measuring over here, we are measuring the phase voltage, and that is why that is little less than the line voltage, and that is less by root 3 times. So that is why the voltage you are getting over here, that is little less. And if you want to observe the line voltage, let me show it to you. Here I have connected this as a line voltage. Now let's run. So now here this is the line voltage. So the amplitude that we have applied is 100 volt RMS. So you can see that the peak is almost around 145, so the RMS could be 100 volts. Now here the phase delay we have provided is 0. What does this mean, 0 phase delay? That will be clearly understood through the waveform of phase voltage. So let's close it. Let's open it, the waveform of phase voltage. In phase voltage, the A phase is starting with this 0, and that 0 is represented over here. Now instead of this 0, let's say if I'll make it 120. So what we are doing, we are providing delay of 120 degree to this phase, and in order to understand that, just observe the sequence. The first one is yellow, then blue, and then red. Now let's close it, close this too, run this thing and open it. So previously we have seen the sequence that is yellow, blue and red, but now you can see the sequence has changed, that is first blue, then red and then yellow. That means it has shifted by 120 degree, right? So close it. So I think this section is clear to you all. This is the amplitude, phase delay and frequency. Let's make the phase delay 0 again. So the next is time variations of, and here we have 3 possible options. First we'll go for the amplitude. So when we select amplitude, this open again a new selections and new parameters. This one is type of variation, what type of variation we want. So in that we have 4 type of variation. Let's say first we'll go for the table of time amplitude pairs. In this variation, what it will does, it will create a variation in amplitude with respect to time. So here the amplitude values, and that is basically a per unit value, and each value of amplitude corresponding to each value of this time, right? So here you can see per unit 1 at 0 time instant, then per unit will become 0.8 at 0.1 time instant, and then at 0.15 time instant the per unit value will become 1.2, and then again at 0.2 time instant it will become 1.0, right? So let's make it okay and run. So here you can compare at 0.1 time instant the amplitude has reduced to 0.8, and at 0.12 time instant the amplitude has increased to 1.2 per unit, and again at 0.2 it reaches up to 1.0, right? But now this variation is for all the 3 phases. If you want this variation for particular one phase, then what you're supposed to do, from here you're supposed to select variation on phase A only, and then OK. Close it and run again. Open it, make it horizontal zoom. So here you can see up to 0.1 all the phases are same, but after 0.1 phase A is reduced to 0.8, and then phase A is shifted to 1.2, and at 0.2 time instant it is again unity. So by selecting this option you will be able to make changes in only one phase, right? Now let's again open this block. Now we'll go for the second option, and that one is step.
Here what you supposed to add, you supposed to add the step magnitude. Here we are providing step magnitude of 0.5. Starting time and ending time, let's say starting time is 0.5 and ending time is 0.8, right? So at 0.5 the step will start, and at 0.8 the step will again come back to its normal position. Let's make it okay, run. So here you can see, so at 0.5 time instant the output is increased by 0.5, or it will add 0.5 into the rated voltage. But now what if you want to reduce magnitude by 0.5? Then over here you supposed to write minus 0.5. Say okay, run again and open. So when you have provided minus 0.5, the magnitude will reduce by 0.5 from 0.5 to 0.8 time instant, or whatever time instant you have provided. Close it again. So here what happens when you select a step variation that you have seen, and I think that is clear to you. The next is ramp. The rate of ramp is provided 10, right? And start and end time will keep the same, 0.5 and 0.8, right? It is the starting and ending time. Let's close it, run again, and here you can see at 0.5 to 0.8 the ramp of 10 increases the voltage with the predefined slope, and that slope is 10, and then after it will be constant with the previous magnitude. Now close it again, let's open it. Now I'll go for the third one, and that is modulation. In modulation it will multiply a modulated signal with the current supply. Let's say the amplitude that we supposed to modulate, that is 0.5, and modulation frequency, let's say we are keeping it 20, right? And we want to modulate, we want to integrate this change in between 0.5 and 0.8. Let's say okay, run again. Now let's see the waveform. So here you can see from 0.5 and 0.8 a signal of 20 Hz frequency and a magnitude of 0.5 is multiplied with this. So this type of variations is created in between these time. Let's say you are changing this frequency to 2 Hz, right? Let's make it okay, run it again and open it. Here you can see the signal of 2 Hz frequency is added with the magnitude of 0.5 with this original signal, and that's how this type of swell you can see from 0.5 to 0.8 time instant. So close it. So here we have seen these varieties of variations that we can create into this voltage source. Now at last we have one more thing, fundamental and harmonic generation or harmonic generation, right? So when you click it, you have few more options, and over here what you're supposed to add, you're supposed to add the order of the harmonics, the amplitude of the harmonics, and phase degree of that harmonics, and you're supposed to say whether that harmonics is 0 sequence, 1 that is positive sequence, and 2 that is negative sequence. So these are the things you're supposed to add. So let's say we have added these parameters. Say okay, run it again and observe the waveform, right? So this is the variation that occurs because of adding of those harmonics. Let's open it. Now close it. Now here we have seen the variations that is possible with the amplitude, but using this programmable voltage source, it is not the only amplitude, but you can make changes with phase and frequency, right? So in these two parameters also you can change the output of this programmable voltage source the way you want. Now I want you to implement these two changes, phase and frequency, and observe what is the change in its output, and then write those observations into the comment of this video, right? Because the length of this video is already being so long, so I am not going to cover these two things in this video. So I wish you implement the changes in phase and frequency and then come back and write your response into the comment of this video, right? So if you have enjoyed this video, do not forget to hit the like button and to subscribe to this channel.
In this video, we are going to learn how to measure active and reactive power in MATLAB. Basically, this session, MATLAB Simulink for beginner, is specially designed who is new to MATLAB Simulink. So in order to measure power in MATLAB, first of all, let's create a simple circuit. For that, let's go to library, simcaps. Now I'm going to create a simple circuit in MATLAB. So this is the simple circuit which is created in MATLAB in order to learn how to measure active and reactive power. Now we'll set the parameters in the circuit. So first of all, we'll start with the voltage source. So here in the voltage source, the peak amplitude is 100 volt. The frequency is 60 hertz. We'll make it 50 hertz. Okay, so we'll keep this parameter as it is. Now we'll go to RLC branch. So here we are going to set RL circuit, right? So that resistance draw active power and inductor draw reactive power. We'll set 10 ohm resistance and 10 millihenry inductor. So now this is our RL circuit is ready. This is current measurement block through which we will measure the current, and this is voltage measurement block through which we will measure the voltage. Now we'll use power GUI block. Now why do we need power GUI block when we're doing simulation? That I have explained in a separate video, and the link is given over here. After this video you can check this out. Now we'll run the simulation, and here you are able to see the voltage and currents waveform. Now we are going to measure active and reactive power. So for that, again we'll go to library. In library we are in measurement block, and over here there is additional measurement. So we'll go to that additional measurement, and in additional measurement there is a block called power. So we'll add this block. So this is the power block. This power block is used to measure electric power in Simulink. It calculates the active and reactive power based on the input voltage and input current. So you can use this block when you want to measure power or you want to analyze the power in a circuit. And not only this block, there is one more block. Let me show you that. One more block is power phasor. So after this I will tell you what is the use of this power phasor. But first of all, let's see how to measure active and reactive power. So here in I will connect the current, and in V will connect the voltage. So here we have voltage and current. So here we have connected power block with the scope. Now let's run. The yellow one is active power and the blue one is reactive power. Now let me show you another block, that is power phasor. So now here we have power phasor. This power phasor block is used to calculate and represent the phasor value of voltage and current signals. And this phasor representation simplifies the analysis of AC system. Now let me show you the output of this power phasor block. But instead of keeping only power phasor output, we'll see it with the current and voltage waveform. So first let me add the waveform of voltage over here, and then I'll add current also. So now here we'll measure power with voltage and current. Let's run. So here this yellow shows the power phasor, this orange one is voltage, and this green one is current. Let me change the inductance so that we can observe the change in waveform. Let's close it. Over here inductance is 10 millihenry, so let's make it 100 millihenry. So you are increasing inductance. So after increasing inductance, you can see that the lagging in current has increased. This one is voltage waveform. The green one over here, let me zoom it a little bit. So now you can see this green waveform. So this green one is current, this orange one is voltage, and this yellow shows the power flow. So that's how you can measure active and reactive power in MATLAB Simulink, as well as you can observe the phasor of power.
For more similar tutorials, you can refer this playlist, Simulink Tutorials. For more tutorials on MATLAB programming, you can refer this playlist, MATLAB Tutorials. So see you in that video. Here you will learn how to measure power factor in Simulink. But the interesting thing is, there is no ready-made block available in Simulink to measure power factor. So now the question is, how to measure power factor in Simulink? So that is what we are going to explore in this video. So let's get started. So now our primary circuit is ready, and in our previous video we have learned how to measure active and reactive power in Simulink, and that measurement we did using two blocks, normal power block and power phasor block. So if you want to explore that, you can check out the previous video from the link given in description or here in I button. So now here we are measuring active and reactive power of the circuit. Now let's run the simulation and observe that this is the active and reactive power that we are measuring. So the yellow one is active power and the blue one is reactive power. Here there is no direct block which can measure power factor in Simulink. So here we'll use whatever we have and we'll get whatever we want. So what do we have right now? Here we have active power and reactive power, and we want power factor. So we can get power factor from this active power and reactive power. Let me show you a small calculation for that. Here this is our active power and the reactive power is 90° to it. And this is the total or apparent power. So in the simulation we are measuring active power and reactive power. The equation for power factor is active power divided by apparent power. And what is the equation for apparent power? Basically the apparent power is S square is equal to active power square plus reactive power square, P square plus Q square. So if we rewrite the equation for power factor, then cos phi is equal to P by S, active by apparent. But what we are measuring? We are not measuring apparent power, but instead we are measuring active power and reactive power. So we'll rewrite this equation as cos phi is equal to P divided by under root P square plus Q square. So this will give us power factor cos phi. So now let's jump back to the simulation. So are you enjoying the simulation journey so far? Don't forget to hit the like button if you found this video helpful. And if you want to stay updated with more exciting Simulink tutorials, make sure to subscribe to our channel. And now let's move forward. So now we are going to use one block which is named as FCN. Basically that is function. So we'll take this FCN block, right? Now we'll take one mux. We'll connect this P and we'll connect this Q. So we are combining two signal and giving this to this FCN. Now we'll open this FCN. We'll remove this expression and write our new expression. Here on the screen you can see the equation that we are going to implement over here. The equation is P. So P is actually our U1. Our first signal is P. So we'll write U of 1. That means our first input divided by, now everything is under root, so we'll write SQRT of U1 square plus U2 square and bracket over. So this is the equation for power factor that we are implementing over here, and let's hit OK. So using this equation, it will convert this power into power factor. So here our power factor is ready. Now we'll add a display. We'll connect this function's output to the display so that we can observe the output. And now you need to pause for a moment and tell me whatever quantity we are going to observe in this display, that quantity is which, whether it is cos phi or it is phi. So write the answer in comments below so that I can identify that how much attentive you are in this video. So now it's time to reveal the answer. The quantity we'll observe over here, that will be cos phi, right? That is power factor. So now let's run this, and you can see over here the power factor is 0.92, and over here you can see the active power is 20 watt and reactive power is 10 VAR. Now let me increase the reactive power to 30 VAR. So here you can see the reactive power is more and active power is less. And now let's find out the power factor. Now there is another question. If I am increasing reactive power, what should be the change in power factor? Whether it will increase or it will decrease from here. What do you think? Write the answer in comments below, and then we'll see how many of you are right. Now let's run. So the updated answer is 0.66. So the power factor will reduce when we increase the reactive power. Now from this power factor you can even find out the angle, and to find out the angle from this you have to do this. Let's say A cos. So this A cos just simply does inverse of cos. So the A cos is connected over here. Now we'll take another display, we'll connect it, and now let's run. The angle shows 0.83 around. Okay, so this angle is in radian, so we're supposed to convert it into degree. So let's remove it. So we have added a gain block. Now in order to convert from radian to degree, you're supposed to multiply it with gain of 360 by 2 pi. Okay, now let's run. Oh my god, it's 474. It's not the correct answer. Let me open it. Okay, so this is the mistake that I did. I supposed to make a bracket over here, and now let's run. Okay, so the angle is 48 degree and the power factor is 0.66. Let me change it again. Now I am making reactive power 0. So when the reactive power is 0, what should be the power factor? Any guesses? Write your guesses in comments and we'll see it now. The power factor is unity and the angle is 0. Change it again, and the result is in front of you. So this is how you can measure power factor in Simulink.
Here we are going to explore how to do THD analysis in Simulink, total harmonic distortion analysis in Simulink. So first let's prepare a simple circuit where we are going to use a sine wave block to create a fundamental frequency and other harmonic frequencies also. For that we'll go to library. In library we'll go to sources. From sources we'll take this sine wave block, we'll add it, minimize it. Now here we have a sine wave block. Open this block. There are various parameters in this block. We'll make amplitude as let's say 10. Now frequency we want to keep as 50 Hertz. Here the frequency is in radian per second. So what we'll do, 50 Hertz multiply by 2 into pi. So 52 pi is 50 Hertz frequency in radian per second. So let's, okay, now we'll have a scope. We'll run it for only 2 cycles. So here we have 50 Hertz frequency is fundamental signal. Now let's close it. Now again we'll go to library, math operator, and here we'll use this add block. We'll give amplitude as 1. Let's say we'll make it third harmonic, so 150 Hertz frequency. We'll make this one amplitude 1 and we'll make it 300 Hertz. Again we'll make the amplitude as 0.5 and 450 Hertz. Again amplitude 1, 600 Hertz. So here we have added various frequencies of sine wave with fundamental frequency with different amplitude, and now we are going to see the resultant output waveform. Let's run it. So here we have created the final distorted signal, and now it's time to do the THD analysis. For that we are going to use this power GUI block. So we are going to do the THD analysis of a final signal using FFT analysis tool, and that tool is part of this power GUI block. We'll go to this tools, and here you can see the FFT analysis tool. Now apart of this, have you ever wondered what is the use of power GUI block in Simulink? There are many simulations in which you cannot run the simulation without using power GUI block. So it's been really interesting to know the need of power GUI block in Simulink. So explore the need of power GUI block in my another video, and the link of that video is in description and here in I button. So now let's get back to this video. So we are going to do the FFT analysis. So for that, let's close it. We'll run it for 1 second. We'll open the scope, go to settings, logging, log data to workspace. We'll name this data as THD. Let's save it, close it. Now we'll take one more scope. In this scope, we are going to connect the fundamental signal, right? We'll open the scope, goes to settings, logging, and here we are going to give the name of this data as fundamental. Now let's run. Now let's open the power GUI block, tools, FFT analysis. When you open the FFT analysis, this type of power GUI FFT analysis tool window will pop up. Now here in this window, this section is to select a particular signal, and this left hand side area is to observe the selected signal. Below that, here we are going to observe the FFT settings, through which we are going to adjust the way we want to observe the FFT analysis, and that analysis part you will be able to see over here. So first we have two types of data, one is fundamental, the another one is THD. So we are going to do analysis of this THD. If you select the fundamental signal will be selected, and if you select the THD, the distorted signal you will be able to see. Now in the scope we are giving only one input. If we are giving multiple input, that multiple input you will be able to see over here. And then in that multiple input, if you are giving a three-phase signal, then individual phase could be selected from this.
Hey there, I am thinking to provide two things. First, a free certification MATLAB course, and a second, in-depth structured course with exclusive content, exercise and support which goes beyond what it's available here, and that is paid MATLAB course. So please let me know by commenting or filling out the interest form in description box below whether you are interested in free certification course or in paid course. Thank you so much.
Now this is the setting for display. If you select the signal, entire signal is selected, and this red one is the selected signal. If you want to observe only selected signal, then you have to select the FFT window. So here we are going to select only signals. Now below that, here we have the FFT settings. The first is start time, from where you want to start the FFT signal. So it is starting from 00, that is why our selected signal is starting from 0. If we want to start from 0.5, then we'll mention 0.5 over here. So the selection of signal will start from here. How many cycles we want to include, and this is the fundamental frequency. The signal that we have created has fundamental frequency of 50 Hz, and here by default it is 60 Hz. So we'll update it to 50 Hz. and then we'll see the number of cycle. Here only one cycle is selected to do the FFT analysis. To make it more precise, you consider multiple cycle. Let's say here I am considering 5 cycle. So these are the 5 cycle which this FFT toolbox will consider to do the FFT analysis. Now the next thing is maximum frequency. The maximum frequency shows in this FFT analysis is 1000 Hertz. If you want to go even further, you can modify it from here. Let's say if you want to go up to 2000, you can select it 2000 and click on display. So here you can see instead of 1000, a maximum frequency of 2000 is being updated. So let's make it 1000 again. So the next is maximum frequency for THD computation. Here we have two options, same as maximum frequency or Nyquist frequency. By default we have the Nyquist frequency option and we are going to use the same one. The next is display style. Here you have varieties of display style. This display style is nothing but the way you are visualizing or presenting the FFT result. Here we have two options, either we can go for bar type visualization or we can go for list type visualization. Now if you observe this thing closely, you can see there are three types of variation. The first one is relative to fundamentals, the second one is specified base, and the third one is relative to DC component. So this relative to fundamental frequency means when analyzing the frequency component of a signal, the fundamental frequency is the lowest frequency component and serves as the base frequency for other harmonics. And displaying the result relative to fundamental frequency means that the magnitude of other frequency component will be presented in relation to the strength of fundamental frequency. So this can help you to understand the harmonic structure of the signal. Till now, are you enjoying the simulation journey? And don't forget to hit the like button if your answer is yes. If you want to stay updated with more exciting simulation tutorials, make sure to subscribe to our channel and join me on Telegram for question and answer and downloading different simulation files. So now let's get back to the video. In the next option, where relative to specific base, this is likely to refer to a chosen reference or a base frequency other than the fundamental frequency. By selecting a specific base frequency, you can analyze and visualize the harmonics and other components of the signal in relation to the chosen frequency. And the final one is relative to the DC component. The DC component presents the constant or a zero frequency component of a signal. It is often depicted separately in FFT analysis because it provides insight into the average or baseline value of signal. Displaying the DC component can be useful for understanding any DC offset presented in the signal. So this is why we have these three varieties of display style. And now I'm going to show you by selecting different display style what changes it makes in this FFT analysis. So first we are observing this bar view display. So this is bar view. The first one 50 Hertz, it's our fundamental frequency. It's around 150 Hertz. It's 300, 450 and 600. Now instead of this bar, let me select the list display. So here you can see sample time, sample cycles, DC component, fundamental and THD. This is 50 Hertz FND that represents our fundamental component, H2 that shows second order harmonics, H3 that is third order harmonics. Here 150 Hertz is the third order harmonics. Here this 10% represents the relative amplitude to this fundamental frequency. The amplitude of fundamental frequency is 10 and the amplitude of this harmonics is 1. So simply it is 10%. After this we have 300 frequency which is almost 10%. Then 450 5% and 600 is 10%. Now let me change the amplitude of harmonics and let's observe what changes it makes. Let's make the amplitude of third harmonics a little bit more. Let's make it even more. This one is 0.5. Let's make it 1. And this one is 1. So let's reduce it to 0.5. Run. Display. So here you can see when we increase the amplitude of third harmonics, it shows the 30%. The same way sixth harmonics also increased, and this one also increased, and this one also increased. Now instead of this, if we select the bar, it shows like this. The magnitude is gradually reducing. Now we are going to select bar but relative to the specific base. Display. Here our specific base is 1. So you can see the difference in magnitude. Instead of this base value 1, if we change base value to 2, you can see the magnitude of all these things is reduced to half, right? So this is how, by changing the base value, you can have variations in FFT analysis. Now let's select bar relative to DC component. Display. Here actually we do not have any DC component. Let's add some DC component to it. Close it. Going to add a constant block. The magnitude of this constant block is constant. Now let's open this constant block. We'll keep the amplitude of this constant block as 1 as it is. Now let's run. Now we are going to select bar relative to DC component and display. So here you can see our DC component is 100%. So the fundamental is 10,000%. So here it will consider the amplitude of DC component as 100%, and with respect to that DC component, it will show the magnitude of all other fundamental and harmonics components amplitude. If we select a list view, then you can see it is 999% larger. Now let's close it. You can even export this FFT analysis by clicking this export button. This FFT analysis will be exported as a separate figure. You can edit this figure the way you want. You can save it as JPEG or .png file format. You can even edit the properties of this image. Now let me show you. Close this thing. Go to this edit. Here figure properties. Go to the figure properties. In figure properties, you just select any of the component which you want to edit. Let's say we want to edit the title, and if you want to make any changes in this title, you can type it and make changes in this title. You can select different font style, you can change the font style, color, line style, line color. Anything you want to change, you can change it from here. You can even change the color of this bar. Just select this bar, and from here you can give it the color you want. There are so many customizations you can do over here. If you want me to make a separate video on that, then just write in comment section. I'll make a separate video on that customizations. Now let's close this thing. So this is how you can do the FFT analysis of any quantity.
If you are looking to generate code from your Simulink model or from your simulation, then this is the right place for you. Here in this canvas, first we'll prepare a simple model file, and then we'll convert that simulation model into the C code, and that is a very simple process. So first of all, let's start with preparing a simple model. And for that, let me bring a constant block, and then I'm going to bring sine wave, right? So I have one constant block, one sine wave, and then I'll bring one relational operator. So this is our relational operator, and then we want scope. So these are the things that we want. Basically what we are going to do, we are going to compare these two things and we'll see the resulting scope, and then we are going to generate code for this. So you can simply imagine that you have one logic, and using that logic you are going to generate some signal. So this is your simulation, and the same thing you want to write as a C code to program your controller, right? So the same thing you can transfer it to your controller. The same C code which we are going to generate through this, that you can directly implement into that controller. So let's set the parameter, it's 1, that is fine. Amplitude, let's make it 2, right? And we'll take one more relational operator, constant block, and sine wave. but here instead 1 will make it -1.
Hey there, I have provided this complete MATLAB course for free and I hope it is very helpful and valuable for you. After learning from this course or after completing this course, if you find it valuable for you and if you want to appreciate my efforts, please do consider donating. Your support will help me invest more time and resources into making even better tutorials and provide valuable learning experience for you. You can find the donation link in description box below. So thank you so much for your support.
One tip I'm going to give you that in scope, if you want to add second signal, you can directly bring it to the scope and it will automatically make another terminal for the signal number 2. Okay, so our simulation is almost ready. Let's save this file and we'll name it as code generation. Let's observe it. It is not looking appropriate the way we want. Okay, I got it. The problem is with this frequency, right? Let's make it 7 radian per second. And now that's fine. It's looking both the signals that we are getting, right? 1 and 2. So now this much is fine. Okay, so now we are going to generate the code. What I am going to do, I am not going to do any setting. So without doing any setting, we'll directly jump into the generating the code. And then we'll have some error and then step by step we'll solve that error and then we'll reach to our final code. So first you need to go to the configuration parameters. In that you need to go to code generation. Here there are varieties of system that you can select, right? By default it is grt.tlc. We will keep it as it is. We will not make a single change, right? And then MATLAB by default it will suggest us that instead of this system target you should go to something else. And then we'll go to report, create code generation report, commands, symbols, codes and interface. We'll keep it as it is. Okay, and then we'll press Ctrl B and then the diagnostic viewer. It shows us some error. And what is that? First is you may configure the solver option for fixed step solver with an appropriate integration algorithm. So we'll open it. So that's what I'm talking about, right? This type of error it will show when we have not set our initial parameters. So instead of these variable steps, we need to make it a fixed step, and here we need to define any appropriate solver. What I am going to take is this ODE4 Range Kutta method solver. So the first issue is solved, and then it shows select a target that supports a variable step solver such as rsim.tlc. So instead of that by default grt.tlc, what we're supposed to do is we'll go and select rsim.tlc. So here it is rsim.tlc. Okay, that's fine. And then you can use embedded code quick start. So we'll open it. This is embedded code quick start. You can use this app from the app store of this MATLAB, but we are using it from here. So our system model, that's fine. Let's jump to next. Which code we want? C, C++ or anything else? So we want C code. The next is deployment. These are the analysis of our code. The analysis is complete. These are the basic detail of our system. And here you need to select execution for efficiency or RAM efficiency. Generally for small system, execution for efficiency, that's fine. And here these are the different files that it will generate. Next, and the system is working to generate the code, right? It will take some time to generate the code, and here we go. Code generation is complete. View code generation report. So here we'll jump to the code generation report. So this is our report. These are the basic information of our generated code.
system report, code interface report. These are the different things. What we are interested in, it is main file. It is ert_main C. This is our main C file. This is our code. This code you can use directly into your controller. So just copy this code and paste it in your controller and you can use the logic directly.